For much of modern astronomy, the history of the universe seemed to follow a remarkably elegant pattern. The Big Bang marked the beginning. Matter gradually cooled. Gravity patiently gathered enormous clouds of gas. The first stars ignited, and only after countless generations of those stars did the great galaxies we know today slowly emerge. It was a story built over decades, refined by observations from ground-based observatories orbiting telescopes and increasingly sophisticated computer simulations. Each new discovery appeared to strengthen the same broad picture. The universe matured gradually, one careful step at a time. Yet the deeper we have begun to look into space, the less certain that comforting picture has become. The James Webb Space Telescope was built to peer farther into the cosmos than any observatory before it, collecting light that began its journey more than 13 billion years ago. By doing so, it offers something extraordinarily rare. It allows us to observe the universe not as it is today, but as it appeared when it was still astonishingly young. Many astronomers expected those first glimpses to reveal small, chaotic collections of newly formed stars, fragile galaxies only beginning their long evolution. Instead, the distant universe has offered something rather different. Some of the earliest galaxies appear brighter, larger, and more developed than many theoretical models anticipated. Their light suggests that within only a few 100 million years after the Big Bang, enormous structures may already have existed where simpler ones were expected. They do not necessarily overturn everything cosmologists understand. In fact, many of the foundations of modern cosmology remain remarkably successful. Yet these observations quietly ask whether one important chapter in the story unfolded differently than we once believed. That distinction matters. Science rarely advances because an old idea suddenly collapses. More often, progress begins with small inconsistencies, a single unexpected measurement, a handful of observations that refuse to fit comfortably inside familiar explanations. Most eventually find their place within existing theories. Occasionally, however, they reveal that nature has been following a more subtle path all along. Astronomy has experienced moments like this before. When distant galaxies were first shown to be moving away from one another, the universe itself expanded beyond humanity's imagination. When invisible gravitational effects hinted at unseen matter, astronomers accepted that most of the cosmos could not be directly observed. When faint microwave radiation filled every direction in space, it became one of the strongest pieces of evidence that the universe had once been unimaginably hot and dense. Each discovery answered one profound question while quietly creating another. The James Webb Space Telescope now continues that tradition. Unlike previous observatories, Webb was not designed simply to produce sharper images. Its greatest strength lies in detecting infrared light wavelengths that stretch beyond ordinary human vision. During their journey across billions of years, the expansion of the universe slowly stretches visible light into the infrared. By observing these faint signals, Webb effectively opens a window onto an era that no human instrument had previously explored in comparable detail. This makes every observation something more than a photograph. Each tiny point of light represents a message carried across almost the entire history of the cosmos. Long before Earth existed, before the Sun formed, before the Milky Way resembled the galaxy we know today, these ancient photons began travelling through expanding space. They crossed immense cosmic distances without knowing that one day they would be captured by a mirror orbiting a quiet point beyond the moon. Those ancient photons now tell stories that astronomers are only beginning to understand. Some reveal galaxies rich with stars far earlier than expected. Others hint at surprisingly organized structures emerging from a universe that should still have been in its cosmic infancy. Measurements continue to improve, interpretations continue to evolve. Some early estimates have already been revised as more precise data become available. Several galaxies once believed to be impossibly distant have turned out to be somewhat closer than initially thought. Yet even after these corrections, important questions remain. How rapidly could galaxies truly assemble? How efficiently could the first generations of stars convert enormous clouds of hydrogen into brilliant islands of light? Could early conditions have allowed galaxies to grow far faster than today's simulations predict? Or do these observations suggest that some assumptions within our models of galaxy formation deserve careful reconsideration? Notice that none of these questions require abandoning everything we know. One of the quiet strengths of science is its willingness to separate confidence from certainty. General relativity continues to describe gravity with extraordinary precision. The expansion of the universe remains supported by multiple independent observations. The Big Bang continues to provide the best overall explanation for the observable cosmos, yet within that broad framework lie many details still waiting to be understood. Galaxy formation has always been among the most complex of them, involving gravity, dark matter, gas dynamics, star formation, black holes, magnetic fields, and processes that unfold across billions of years. Even the most advanced supercomputers can only approximate that complexity. This is why astronomers respond to surprising discoveries with cautious excitement rather than immediate conclusions. Every unexpected observation becomes an invitation to ask better questions. Sometimes improved measurements resolve the mystery. Sometimes theoretical models adapt naturally, and occasionally the universe reveals that it has been more creative than human imagination anticipated. The James Webb Space Telescope has not rewritten the history of the cosmos. Not yet. What it has done is illuminate a chapter that was previously hidden almost entirely from view. Like opening an ancient manuscript whose earliest pages had long been missing, Webb allows us to read the beginning of a story that humanity has only partially understood. Some passages now appear exactly as expected, others seem unfamiliar, hinting that the opening chapters may contain complexities that generations of astronomers could never directly observe until now. Over the course of this journey, we will follow those faint streams of ancient light across billions of years. We will trace how astronomers built the modern picture of cosmic evolution, why that picture has been remarkably successful, where the newest observations create genuine uncertainty, and how evidence, not assumption, guides every step toward deeper understanding. Because before we can decide whether these distant galaxies truly should not exist, we must first understand why anyone believed they could not. For centuries, the night sky appeared timeless. The stars rose and set with remarkable consistency. Constellations retained their familiar shapes across generations. The pale ribbon of the Milky Way stretched across the darkness much as it had for countless civilizations before us. To the human eye, the universe seemed complete, almost permanent, as though it had always existed in roughly the same form. It is easy to understand why this view endured for so long. Our lives unfold over decades. Civilizations rise and fall over centuries. Even mountains change only gradually within the span of recorded history. Against these brief measures of time, the cosmos appears almost frozen. The stars seem eternal because their true lifetimes are measured not in years, but in millions or even billions of years. Only during the past century did astronomers begin to realize that the universe is not a static stage upon which history unfolds. It has a history of its own. That realization forms the foundation of everything that follows. Today, the standard cosmological model describes a universe that has been expanding for approximately 13.8 billion years. This number is not a simple estimate or a convenient round figure. It emerges from several independent lines of evidence that agree remarkably well with one another. Observations of distant galaxies, measurements of the cosmic microwave background, the abundance of the lightest chemical elements, and the large-scale distribution of galaxies all converge on a common story. The universe has changed continuously since its beginning. To appreciate why Webb's discoveries are so intriguing, we must first understand that familiar story not because it is flawless, but because it has explained an extraordinary amount of what we observe. The earliest moments after the Big Bang remain among the least understood chapters in cosmology. Physics can describe conditions beginning a tiny fraction of a second after the initial expansion. But what occurred at the very beginning remains an open scientific question. Rather than pretending certainty where none exists, Astronomers simply acknowledge that the earliest instant lies beyond the reach of current evidence. As the newborn universe expanded, it also cooled. In its infancy, temperatures were so extreme that atoms could not exist. Matter was compressed into a dense plasma of elementary particles and radiation. Photons constantly collided with charged particles, preventing light from traveling freely. The universe was not dark because there was no light. It was opaque because light could not move very far before being scattered again. For hundreds of thousands of years, this condition persisted. Then, as temperatures continued to fall, something profound occurred. Electrons slowed enough to combine with atomic nuclei, forming the first stable hydrogen and helium atoms. Suddenly, photons were no longer trapped by countless collisions. Light began traveling freely across space. That ancient light still surrounds us today. Known as the cosmic microwave background, it is one of the oldest observable signals in existence. It is not merely a relic of the past, but a snapshot of the universe when it was only about 380,000 years old. Tiny variations within this faint glow reveal slight differences in density that would eventually become the seeds of every galaxy, every star, every planet, and every living creature. The early universe was surprisingly uniform, yet it was not perfectly uniform. Those minute irregularities were essential. If matter had been distributed with absolute perfection, gravity would have had nothing to amplify. The cosmos might have remained an almost featureless sea of gas forever. Instead, regions containing just slightly more matter exerted slightly stronger gravitational attraction. Over immense spans of time, those tiny advantages grew larger. Gravity is patient. It does not rush. Given enough time, however, even the smallest imbalance can reshape an entire universe. Slowly, clouds of hydrogen and helium drifted toward one another. Invisible concentrations of dark matter deepened these gravitational wells, providing the scaffolding upon which ordinary matter could accumulate. Although dark matter has never been observed directly, its gravitational influence appears throughout the cosmos. Without it, the structures we see today would be extraordinarily difficult to explain. As gas collected inside these invisible halos, pressure and temperature gradually increased. Eventually, the first stars ignited. These earlier stars were unlike most stars alive today. Formed almost entirely from hydrogen and helium, they contained virtually none of the heavier elements that later generations would inherit. Many astronomers believe they were enormous, exceptionally hot, and relatively short-lived. Their intense radiation transformed their surroundings, while their violent deaths forged the first heavier elements that future stars and planets would require. The universe had entered a new age. With stars came galaxies. Not fully formed spiral galaxies like the Milky Way, but smaller systems that gradually merged, collided, and grew. Gravity pulled neighboring structures together. Gas continued feeding new generations of stars. Supernova explosions enriched interstellar clouds with carbon, oxygen, silicon, iron, and countless other elements that had not existed during the universe's earliest moments. Each generation prepared the way for the next. Over hundreds of millions, and then billions of years, galaxies became increasingly massive and complex. Some developed elegant spiral arms. Others evolved into giant elliptical systems filled with ancient stars. Supermassive black holes formed within many galactic centers, influencing the evolution of entire galaxies through processes astronomers are still striving to understand. Our own Milky Way became one chapter within this larger cosmic history. Around 4.6 billion years ago, one cloud inside a spiral arm collapsed to form the Sun. Leftover material assembled into planets, moons, asteroids, and comets. On one small rocky world, chemistry eventually became biology. Much later, that biology evolved into beings capable of asking how the entire sequence began. It is a breathtaking chain of events. Yet what makes this narrative scientifically powerful is not its beauty. It is its predictive ability. Long before the James Webb Space Telescope was conceived, astronomers built computer simulations based on these physical principles. Starting with the tiny fluctuations visible in the cosmic microwave background, they allowed gravity, dark matter gas dynamics, and cosmic expansion to shape a virtual universe. Again and again, these simulations produced structures remarkably similar to the large-scale universe we observe today. Galaxy clusters emerged, filaments stretched across hundreds of millions of light-years. Vast cosmic voids appeared between them. Even the statistical distribution of galaxies matched observations with impressive accuracy. This success gave astronomers confidence that they understood the broad outline of cosmic evolution. Not every detail, certainly. Galaxy formation remains extraordinarily complicated. Star formation depends on turbulent gas magnetic fields, radiation, stellar winds, black hole activity, and countless interactions occurring simultaneously across enormous ranges of scale. No simulation captures every process perfectly. Nevertheless, the general expectation remained consistent. The earliest galaxies should have been relatively small. Large, mature galaxies would require time to grow through mergers, sustained star formation, and the gradual accumulation of matter. Complexity, according to the prevailing picture, was something the universe earned slowly. That expectation was not arbitrary. It arose naturally from decades of successful theory supported by multiple independent observations, which is precisely why the first deep images from Webb attracted so much attention. Because if the earliest galaxies truly appeared more massive, brighter, or more evolved than expected, the question was not simply whether the telescope had discovered something unusual. The deeper question was whether the opening chapters of cosmic history unfolded more quickly than anyone had realized. And before answering that possibility, we must understand exactly how a telescope positioned more than 1 million kilometers from Earth is able to observe light that has been traveling since almost the beginning of time. The history of science is filled with moments when nature appeared to agree perfectly with our expectations. Then, almost imperceptibly, small exceptions began to appear. At first, they rarely seemed important. A measurement differed slightly from prediction. An observation resisted a straightforward explanation. An experiment produced results that could not easily be repeated. Most of these discrepancies eventually disappeared as instruments improved or hidden sources of error were uncovered. Yet every now and then one of those quiet inconsistencies survived. Rather than fading away, it grew clearer with every new observation. Astronomy has experienced this pattern many times. The discovery of Neptune began with tiny irregularities in the orbit of Uranus. Dark matter emerged because galaxies rotated faster than visible matter alone could explain. Dark energy entered cosmology after distant supernovae revealed that cosmic expansion was accelerating rather than slowing. Each mystery began not with certainty, but with small cracks in an otherwise successful picture. The James Webb Space Telescope has introduced another such moment, not because it has disproved modern cosmology, not because decades of research have suddenly become obsolete, but because it has shown us regions of the early universe that previous telescopes could barely glimpse. Before Webb, astronomers relied heavily on the remarkable achievements of the Hubble Space Telescope. Hubble transformed our understanding of the cosmos, revealing galaxies whose light had travelled for more than 13 billion years before reaching Earth. Its famous deep-field images contained thousands of galaxies packed into tiny patches of sky that had once appeared almost empty. Those observations already hinted at an astonishing truth. The farther we looked into space, the younger the universe became. Yet Hubble faced an unavoidable limitation. As the universe expands, light travelling across billions of years becomes stretched. Wavelengths gradually lengthen, shifting from visible colours into infrared radiation. Some of the oldest galaxies emit light that arrives almost entirely beyond the range where Hubble was most sensitive. It was rather like trying to read the oldest pages of a book while several of the first chapters remained hidden beneath a sheet of paper. Webb was built specifically to lift that sheet. Its infrared instruments could reveal galaxies that had previously been little more than faint suggestions buried within background noise. Astronomers knew they would find more galaxies. What they didn't know was exactly what those galaxies would look like. Computer simulations had offered reasonable expectations. The earliest galaxies should generally be compact. They should contain relatively modest amounts of stellar mass. Their stars should still be assembling. Large-scale structure should exist, but only in its earlier stages of development. The first images seemed at first glance to satisfy many of these expectations. Countless faint galaxies emerged from darkness exactly where theory predicted they would. But hidden among them were objects that attracted immediate attention. Some appeared unexpectedly bright. Brightness alone does not necessarily indicate enormous size. A galaxy can shine intensely because it contains vigorous star formation, an active central black hole, or unusually massive young stars. Brightness is only one clue among many. Still, it was enough to encourage closer examination. As astronomers analysed these ancient galaxies, they began estimating distances using a technique known as photometric redshift. Here it is helpful to pause for a moment. Light behaves much like the sound of a passing train. As the train moves away, its sound becomes lower in pitch because its waves stretch. Light experiences something similar as space itself expands. Instead of changing pitch, its wavelength becomes longer, shifting toward the red end of the spectrum. This phenomenon is called redshift. The greater the redshift, the farther light has travelled, and the earlier in cosmic history we observe the object. Initially, several galaxies appeared to possess astonishingly large redshifts. If correct, they would have existed only a few 100 million years after the Big Bang. Even more surprising were estimates of their apparent masses. Some analyses suggested stellar populations far larger than many theoretical models had predicted could exist so early. News headlines soon followed. Galaxies that should not exist. Impossible galaxies. Cosmic surprises rewriting the universe. The reality, as is often true in science, was more measured. Photometric measurements are powerful, but they are also provisional. They estimate distance by measuring brightness through multiple filters and comparing the resulting colours with theoretical models. While remarkably effective, this approach can sometimes mistake a nearer dusty galaxy for a much more distant one. Astronomers therefore sought something more reliable. Spectroscopy. Instead of measuring overall colour, spectroscopy separates light into its individual wavelengths, revealing distinctive fingerprints produced by atoms and molecules. These spectral features allow astronomers to determine redshift with far greater confidence. One by one, Webb's spectroscopic instruments revisited many candidate galaxies. Some of the earliest claims became less dramatic. Several galaxies turned out to be somewhat closer than originally believed. Others contained somewhat lower stellar masses than initial estimates suggested. These corrections were important. They demonstrated exactly how science should work. Extraordinary claims are tested. Measurements improve. Interpretations evolve. Yet something equally important also happened. Not all of the tension disappeared. Even after improved measurements, astronomers continued finding galaxies that seemed surprisingly luminous for such an early epoch. Some displayed vigorous star formation occurring at extraordinary rates. Others contained unexpectedly evolved stellar populations. Meanwhile, another mystery quietly emerged. Supermassive black holes also appeared to be growing astonishingly rapidly during the universe's first billion years. This raised an uncomfortable possibility. If galaxies and black holes both developed faster than expected, perhaps they were responding to underlying physical processes that current models did not fully capture. Or perhaps our assumptions about early star formation required refinement. The question was becoming increasingly subtle. No longer was it simply whether galaxies existed. Of course they did. The issue was how quickly they assembled, how efficiently gas collapsed into stars, how rapidly black holes accumulated mass, how effectively dark matter halos gathered ordinary matter during the earlier stages of cosmic history. Each of these processes depends upon complicated interactions. Gas cools, gravity compresses it, stars ignite, radiation heats surrounding clouds, supernova explosions both enrich and disrupt star-forming regions. Black holes release enormous amounts of energy. Each influence competes with the others. Changing even one ingredient slightly can alter the entire pace of galactic evolution. This complexity explains why astronomers remained cautious. The standard cosmological model had not failed. Far from it. Its predictions continued matching observations across an extraordinary range of scales, from the cosmic microwave background to the distribution of galaxy clusters. What Webb had revealed was not necessarily contradiction. It was a challenge, specifically a challenge to understand the detailed physics governing the universe's earliest generations of galaxies. As additional observations accumulated, a fascinating picture began to emerge. Some of the earliest galaxies may have converted gas into stars far more efficiently than many simulations had assumed. Others may contain stellar populations whose light makes them appear more massive than they truly are. Still others may owe part of their brilliance to active supermassive black holes hidden within their centers. None of these possibilities has yet provided a complete explanation. Each accounts for part of the evidence. None explains every observation. That is precisely why the mystery remains alive. The first cracks in our familiar picture have not widened into a collapse. Instead, they have opened a narrow window through which astronomers can glimpse processes that were previously invisible. And to understand why that window exists at all, we must first understand the remarkable observatory that made these discoveries possible. A telescope engineered not merely to see farther than Hubble, but to capture some of the oldest surviving light in the entire universe. Long before the James Webb Space Telescope ever observed its first galaxy, it existed as an ambitious idea. Astronomers understood that every generation of telescopes had expanded humanity's view of the universe. Galileo revealed that Jupiter possessed its own moons. Large ground-based observatories mapped distant nebulae. The Hubble Space Telescope transformed faint smudges into countless galaxies, showing that the observable universe was far richer than anyone had imagined. Yet even Hubble approached a natural limit. The oldest galaxies emit light that has travelled for more than 13 billion years. During that immense journey, the expansion of space steadily stretches every wavelength. Light that originally left those galaxies as visible ultraviolet radiation arrives today as infrared light. To observe the earliest chapters of cosmic history clearly, astronomers needed an observatory designed specifically for those stretched wavelengths. That requirement shaped every aspect of Webb's design. Unlike Hubble, which circles Earth only a few hundred kilometers above the surface, Webb operates far beyond the Moon. Its destination is known as the Second Lagrange Point, or L2, located roughly 1.5 million kilometers from Earth. This is not a physical object, but a region where the gravitational influence of Earth and the Sun allows a spacecraft to remain in a relatively stable position while orbiting the Sun alongside our planet. From there, Webb enjoys a remarkably quiet environment. The Sun, Earth, and Moon all remain on nearly the same side of the telescope. This arrangement allows an enormous sunshield to block their heat, simultaneously keeping the scientific instruments permanently pointed toward the cold darkness of deep space. For an infrared telescope, cold is not simply desirable. It is essential. Every warm object emits infrared radiation. Human beings do. The Earth does. The telescope itself does. If Webb became too warm, its own heat would overwhelm the faint signals arriving from galaxies formed near the beginning of cosmic history. Detecting those ancient photons would be like trying to observe the glow of a distant candle while standing beside a roaring bonfire. The solution was extraordinary. Webb carries a 5-layer sunshield roughly the size of a tennis court. Each thin layer reflects and radiates heat away from the spacecraft, reducing temperatures dramatically as one moves from the sun-facing side toward the scientific instruments. On the hot side, temperatures can exceed 100 degrees Celsius. On the cold side, many instruments operate near minus 230 degrees Celsius. Across only a few centimeters of layered material exists one of the most remarkable temperature differences ever engineered into a scientific spacecraft. Building such an observatory was never straightforward. Unlike previous space telescopes, Webb could not fit inside a launch vehicle in its operational form. Its primary mirror, measuring 6.5 meters across, had to fold for launch and unfold perfectly after reaching space. The mirror itself consists of 18 hexagonal segments made from beryllium, chosen because it remains exceptionally stable at extremely low temperatures. Each segment is coated with an incredibly thin layer of gold, not because gold appears luxurious, but because it reflects infrared light with remarkable efficiency. Together, these 18 mirrors function as a single optical surface. Achieving that required astonishing precision. After launch, tiny actuators behind every mirror segment adjusted their positions by fractions of the width of a human hair. At first, each segment produced its own separate image of the same star. Gradually, through weeks of careful alignment, those 18 images merged into one perfectly focused point. It was rather like tuning an orchestra. Each instrument might play beautifully on its own, but only when every performer is precisely synchronized does the full symphony emerge. The deployment itself became one of the most delicate engineering sequences ever attempted beyond Earth. Hundreds of individual mechanisms had to operate correctly. The sun shield unfolded. Its supporting booms extended. Thousands of cables tightened each protective layer. The mirror wings rotated into position. Secondary support structures locked into place. Many engineers referred to these operations with quiet respect because there was no practical way to repair the telescope if something failed during deployment. For weeks, every successful step represented another carefully crossed threshold. When Webb finally became fully operational, attention shifted from engineering to science. Its 4 primary scientific instruments offered capabilities unlike any previous observatory. Near-infrared cameras could detect some of the faintest galaxies ever observed. Spectrographs could separate ancient light into detailed spectra, allowing astronomers to measure redshift chemical composition temperature and the motion of distant objects. Additional instruments extended observations farther into the mid-infrared, revealing cool dust forming stars, planetary systems, and galaxies hidden behind thick clouds that visible light cannot penetrate. Webb was never intended to study only the distant universe. It examines planets within our own solar system. It analyzes the atmospheres of planets orbiting other stars. It observes newborn stellar nurseries where future suns are taking shape. It investigates dying stars surrounded by expanding shells of gas. It traces the chemistry of interstellar clouds that may eventually produce new generations of planets. Yet among all these objectives, one scientific goal captured particular imagination: to observe the first galaxies. Not by reconstructing them through theory alone, but by collecting the actual light they emitted billions of years ago. This distinction is profound. History is usually reconstructed through fragments. Ancient civilizations leave ruins. Extinct animals leave fossils. Early human cultures leave tools, artwork, and scattered bones. Astronomy is different, because light requires time to travel. Observing distant galaxies allows us to witness earlier moments directly. We do not excavate cosmic history from buried remains. We intercept messages that have been traveling continuously since those events occurred. Every photon arriving at Webb is therefore a traveler from another age. Some began their journey before the Milky Way acquired much of its present structure. Others departed long before the Sun existed. Some left galaxies whose modern descendants may now look entirely different after billions of years of mergers, star formation, and evolution. This ability makes Webb less like a conventional telescope and more like a time machine built according to the laws of physics, not one that carries observers into the past, one that allows the past to arrive naturally carried by light itself. Even so, astronomers knew that extraordinary images alone would not answer the deepest questions. Beautiful photographs inspire curiosity. Precise measurements produce understanding. Brightness must become stellar mass. Color must become chemical composition. Patterns must become evidence. Only then can observations be compared with theoretical models describing how the earliest galaxies formed. As Webb's first observations accumulated, astronomers began assembling one of the most detailed portraits ever created of the infant universe. And with every newly measured galaxy, another realization quietly emerged. The farther into cosmic history Webb looked, the closer it came to the moment when the very first galaxies began to shine. The next challenge was no longer simply building the telescope. It was learning how to read the extraordinary messages carried by the oldest light in existence. Every photograph captures a moment that has already passed. Even the image on a modern smartphone is never truly happening in the present. By the time light reflects from a face traveled through the lens, reaches the sensor and appears on the screen, a tiny fraction of a second has already elapsed. In everyday life, the delay is so small that it goes unnoticed. Across the universe, that delay becomes the very foundation of astronomy. Light has a finite speed. It travels at nearly 300,000 kilometers every second, fast enough to circle Earth more than 7 times in the time it takes to blink. Yet even at this extraordinary speed, the cosmos is so immense that light requires years, centuries, or even billions of years to cross it. When we look at the moon, we see it as it was about 1¼ seconds ago. The sun appears as it was roughly 8 minutes in the past. The nearest star beyond our solar system is seen more than 4 years ago. The Andromeda Galaxy appears as it existed about 2.5 million years before the first humans appeared. Distance in astronomy is inseparable from time. Every increase in distance is also a deeper step into history. This is one of the most remarkable consequences of living in an expanding universe. Unlike archaeologists who uncover ancient civilizations by digging downward through layers of soil, astronomers uncover cosmic history simply by looking farther away. The farther they observe, the younger the universe becomes. At first, this idea can feel almost paradoxical. The galaxies that Webb studies still exist somewhere in the modern universe. During the billions of years that their light has been travelling toward us, they have continued evolving. Stars have lived and died. Black holes have grown. Neighbouring galaxies have collided. Entire galactic structures have changed beyond recognition. But none of those later events can affect the light already travelling toward Earth. Those photons carry only the information available at the instant they departed. It is rather like receiving a letter mailed many years ago. The author may have experienced countless events since writing it, yet every word preserves a single frozen moment in time. The letter cannot update itself during its journey. Ancient light behaves in much the same way. Every photon becomes a historical document. This simple fact transforms Webb into far more than a powerful camera. It becomes a chronicle of cosmic evolution. Instead of observing one galaxy repeatedly as it ages, astronomers examine enormous numbers of galaxies at different distances. Nearby galaxies reveal mature stages of evolution. More distant galaxies reveal progressively younger stages. By arranging these observations according to cosmic age, scientists reconstruct an evolutionary sequence spanning almost the entire lifetime of the observable universe. No individual galaxy lives through this sequence before our eyes. Instead, countless galaxies together create a timeline. The approach resembles studying forests. No one can watch an oak tree grow from seed to full maturity over centuries. Yet by observing thousands of trees of different ages simultaneously, a complete life cycle becomes visible. The universe offers a similar opportunity. Some galaxies are ancient and well developed. Others are still young. The most distant ones approach the earliest periods when galaxies first emerged from darkness. This raises an important question. How do astronomers know how old these distant galaxies really are? The answer begins with expansion. In the early 20th century, astronomers discovered that distant galaxies are moving away from one another because space itself is expanding. This expansion stretches every wavelength of light crossing the cosmos. Blue light gradually becomes green. Green becomes yellow. Yellow shifts toward red. Eventually, visible light stretches entirely beyond human vision into infrared wavelengths. This phenomenon is called cosmological redshift. It is not exactly the same as the familiar Doppler effect produced by moving objects. Instead of galaxies racing through static space, the space between galaxies itself expands, carrying light along with it. The larger the expansion, the greater the redshift. And the greater the redshift, the earlier the light was emitted. Astronomers use this relationship as one of their most powerful tools. When Webb observes a galaxy whose spectral features have shifted dramatically toward the infrared, it is detecting light that began its journey when the universe was only a small fraction of its present age. Yet measuring redshift is only the beginning. Once distance is established, astronomers can begin asking more detailed questions. How bright is the galaxy? How rapidly are new stars forming? How much gas remains available for future star formation? What chemical elements are already present? Does the galaxy contain large amounts of dust? Is a supermassive black hole actively feeding at its center? Each answer contributes another piece of the puzzle. Chemical composition is especially revealing. The earliest universe contained almost entirely hydrogen and helium. Heavier elements such as carbon, oxygen, magnesium, silicon, and iron did not exist immediately after the Big Bang. They were manufactured later inside stars through nuclear fusion and dispersed by supernova explosions. Every generation of stars enriched the surrounding gas. Future stars inherited those newly created elements. Planets eventually formed from the same material. Life itself depends upon atoms forged within long-dead stars. Because of this process, astronomers often describe heavier elements collectively as metals, even though many are not metals in the ordinary chemical sense. The abundance of these elements tells an important story. A galaxy containing almost no heavy elements likely formed very early, before many generations of stars had time to enrich their surroundings. A galaxy rich in heavier elements has usually experienced a longer history of stellar evolution. Webb's spectroscopic instruments allow astronomers to detect these chemical fingerprints across billions of light-years. Each spectrum resembles a barcode written by nature. Dark absorption lines and bright emission lines identify individual atoms, revealing temperatures, densities, motions, and chemical abundances that cannot be determined from photographs alone. This ability transformed the telescope into a laboratory operating across the observable universe. Rather than merely seeing ancient galaxies, astronomers could begin studying them in remarkable detail. And those details sometimes proved surprising. Some galaxies displayed unexpectedly intense bursts of star formation. Others appeared chemically more evolved than anticipated. A few seemed capable of producing stars at extraordinary efficiency despite existing when the universe was still remarkably young. None of these observations automatically contradicted established cosmology. Instead, they suggested that the earliest chapters of galaxy formation might have been more dynamic than many simulations predicted. Perhaps gas cooled more efficiently. Perhaps dense regions collapsed more rapidly. Perhaps the first stars differed significantly from later generations. Or perhaps several subtle effects combined to accelerate early galactic growth. These possibilities remain active areas of research. Each new observation helps eliminate some explanations while strengthening others. Science advances not by selecting the most exciting hypothesis, but by patiently comparing every idea against evidence. This careful process is especially important when studying the infant universe. The farther we look back in time, the fainter galaxies become. Their light is extraordinarily weak. Sometimes only a handful of photons arrive after travelling for more than 13 billion years. Extracting reliable information from such delicate signals demands remarkable precision and enormous caution. Yet despite these challenges, Webb continues extending humanity's view farther into cosmic history than ever before. Each deeper observation becomes another page recovered from the universe's earliest chapters. And as those pages accumulate, one mystery grows increasingly difficult to ignore. If these young galaxies truly formed stars with such astonishing speed, what physical processes allowed them to grow so rapidly in the first place? That question leads us directly to the heart of the documentary's central mystery. There is a quiet difference between a mystery and a contradiction. A contradiction suggests that two ideas cannot both be true. One must eventually give way. A mystery is more subtle. It begins when observations reveal something that our current understanding does not yet fully explain. The existing picture may remain largely correct, yet an important piece is still missing. History shows that many of science's greatest advances have emerged from precisely this kind of uncertainty. The galaxies revealed by the James Webb Space Telescope belong to that second category. They do not stand outside the laws of physics. They do not require us to abandon the Big Bang. They do not prove that cosmology has taken a wrong turn. Instead, they ask a quieter question. Could the earliest galaxies have grown much faster than we expected? To appreciate why this question matters, it helps to think about the pace of construction. Suppose two cities begin building on the same day. Both have identical supplies of stone, timber, and workers. If one city completes towering cathedrals while the other has only finished a few small houses, we would naturally wonder whether something about the first city was different. Perhaps its workers were more efficient. Perhaps additional resources arrived unexpectedly. Perhaps the original assumptions about the building process were incomplete. The cities themselves would not violate any laws of engineering. They would simply suggest that the story of their construction had been more complicated than we first imagined. Astronomers find themselves asking much the same question about the infant universe. According to the standard picture of cosmic evolution, the first galaxies formed within invisible halos of dark matter. These halos acted like enormous gravitational basins, collecting ordinary hydrogen and helium gas from their surroundings. As more gas accumulated, it cooled, became denser, and eventually collapsed into stars. This sequence is well supported. Computer simulations reproduce it naturally. Observations of galaxies across much of cosmic history agree with it remarkably well. The uncertainty lies not in whether the process occurred, but in how quickly it unfolded. Every galaxy is engaged in a delicate balance. Gravity constantly pulls matter inward. At the same time, newly formed stars release enormous amounts of energy. Their ultraviolet radiation heats surrounding gas. Powerful stellar winds push material outward. When massive stars explode as supernovae, they inject tremendous energy into their environments, disrupting the very clouds from which future stars might otherwise have formed. This creates a natural feedback cycle. Star formation encourages more stars, yet it also limits itself. The more vigorously a galaxy forms stars, the more energy it produces to slow additional star formation. For decades, this self-regulating picture has explained many observations successfully. Galaxies generally do not convert all their available gas into stars at once. They proceed gradually. Their growth unfolds over hundreds of millions or billions of years. Webb's observations hint that at least some early galaxies may have behaved differently. Not completely differently, not impossibly, simply more efficiently. Imagine two campfires. Both begin with identical piles of wood. One burns steadily throughout the night. The other catches immediately consuming fuel with astonishing speed before settling down. Both obey exactly the same laws of combustion. The difference lies only in how conditions influence the rate of burning. Some astronomers suspect the earliest galaxies may have resembled that second fire. The young universe itself may have provided unusually favourable conditions for rapid growth. At that time, the cosmic environment was denser than it is today. Galaxies lay much closer together. Gas flowed more readily into growing dark matter halos. Collisions and mergers occurred more frequently. Fresh material continuously arrived to sustain vigorous star formation. If these conditions were especially favourable, galaxies might have assembled far more rapidly than earlier models estimated. Another possibility involves the first generation of stars. Astronomers believe the earliest stars formed from nearly pure hydrogen and helium, lacking the heavier elements that exist today. These primitive stars, often called population 3 stars, remain one of astronomy's most important missing pieces. Curiously, no confirmed example has yet been observed directly. Their existence is strongly predicted by theory, but they likely lived short, brilliant lives before disappearing billions of years ago. If these stars were substantially more massive than today's stars, they would also have been extraordinarily luminous. A relatively small number of such stars could make a young galaxy appear brighter than expected, without requiring an enormous stellar population. Brightness, therefore, might not always correspond directly to total mass. The distinction is important. Astronomers do not weigh distant galaxies directly. Instead, they estimate mass by interpreting the light those galaxies produce. If early stellar populations differed significantly from modern ones, then some initial mass estimates could naturally require revision. Yet even this explanation may not solve every observation. Some galaxies appear not merely bright but surprisingly structured. Others exhibit chemical signatures indicating that several generations of stars may already have lived and died. That would require enough time for stellar evolution to enrich surrounding gas with heavier elements. Again, nothing impossible, simply unexpectedly rapid. Then there are the black holes. One of the most fascinating developments in Webb's observations has been the growing evidence that supermassive black holes already existed astonishingly early in cosmic history. These objects contain millions or even billions of times the mass of the Sun. Building them should require time. Yet some seem to have formed within the universe's first billion years. Their existence raises questions remarkably similar to those surrounding the galaxies themselves. How did they grow so quickly? Did unusually massive seed black holes form very early? Did gas fall inward at exceptionally high rates? Or are there physical processes still missing from current models? Interestingly, galaxies and black holes appear deeply connected. Nearly every large galaxy observed today contains a supermassive black hole at its centre. The growth of one appears linked to the evolution of the other. If Webb is revealing faster galaxy formation, it may also be revealing faster black hole growth. The two mysteries could be different expressions of the same underlying process. This possibility has become one of the most active areas of modern astrophysical research. Yet throughout these discussions, astronomers remain careful with their language. Words such as impossible or shouldn't exist rarely appear in scientific papers. Instead, researchers describe observations as unexpected, difficult to reconcile with current models, or requiring further investigation. Such caution is not hesitation, it is discipline. The universe owes us no obligation to match our predictions. Likewise, scientists owe the universe no premature conclusions. Every new observation must survive repeated testing. Independent teams analyze the same data. Alternative explanations are explored. Measurements improve. Only gradually does confidence increase. This deliberate pace may seem slow, but it has allowed science to build one of the most reliable bodies of knowledge humanity has ever created. The mystery, therefore, is not whether Webb has broken cosmology. The mystery is whether the earliest universe possessed conditions that allowed galaxies to flourish with remarkable speed while remaining entirely consistent with the deeper laws governing gravity matter and cosmic expansion. To answer that question, astronomers must follow every available clue. Fortunately, the ancient light itself still carries many more secrets. Once a mystery has been identified, science follows a remarkably disciplined path. It does not begin by searching for extraordinary explanations. It begins by asking whether the observations themselves are correct. This habit can seem almost disappointingly cautious. When a surprising discovery captures public attention, there is often an understandable temptation to leap immediately toward bold new ideas. Yet astronomers have learned through centuries of experience that nature is usually more subtle than our first interpretation. Before rewriting any theory, they first examine every possible source of uncertainty. The galaxies observed by the James Webb Space Telescope are no exception. Each distant galaxy begins not as a clear image but as an extraordinarily faint collection of photons. Some of those photons began their journey when Earth did not yet exist. For more than 13 billion years, they crossed expanding space, passed through galaxy clusters, drifted across immense cosmic voids, and finally entered the gold-coated mirrors of Webb. Only then does the real work begin. The telescope converts those tiny flashes of ancient light into digital information. Sophisticated software removes instrumental effects, corrects for detector imperfections, and combines multiple observations into a single image. Even at this early stage, astronomers remain aware that every processing step introduces choices that must be carefully tested. No single image is accepted uncritically. Independent teams often analyze the same observations using different methods. If separate approaches produce similar results, confidence grows. If they differ, the discrepancy itself becomes part of the investigation. This careful verification has become one of the defining strengths of modern astronomy. After an object is identified, researchers ask a deceptively simple question. How far away is it? As we've already seen, distance determines cosmic age. A galaxy observed at a very high redshift is seen during the universe's infancy. One at a lower redshift belongs to a later chapter of cosmic history. The first estimate often comes from photometry. Webb observes the galaxy through several filters, each transmitting a different range of wavelengths. Because hydrogen absorbs ultraviolet light in a characteristic way, extremely distant galaxies display a sudden drop in brightness at specific wavelengths. This feature, sometimes called the Lyman break, provides an initial estimate of redshift. It is an elegant method, yet it is not infallible. Dust within a nearer galaxy can sometimes imitate the colours expected from a much more distant object. Active black holes may alter the observed spectrum. Unusual stellar populations can shift the apparent colours in unexpected ways. For that reason, astronomers seek stronger evidence whenever possible. Spectroscopy provides exactly that. Instead of measuring overall brightness through broad filters, a spectrograph spreads incoming light into thousands of individual wavelengths. Hidden within that spectrum are narrow emission and absorption lines produced by specific atoms. Hydrogen leaves one pattern, oxygen leaves another. Carbon, nitrogen, neon, sulfur, and many other elements each possess their own distinctive signatures. These patterns behave like fingerprints. No two elements produce exactly the same arrangement. When those fingerprints appear shifted toward longer wavelengths, astronomers can calculate the galaxy's redshift with remarkable precision. This transition from photometric estimates to spectroscopic confirmation has already refined many early Webb discoveries. Some galaxies originally believed to be among the oldest known turned out to be somewhat younger. Others remained almost exactly where initial observations had placed them. Both outcomes were scientifically valuable. Corrected measurements improve future analyses. Confirmed measurements strengthen confidence in the observations. Distance, however, represents only one part of the story. Astronomers also wish to estimate stellar mass. This task is considerably more difficult. Unlike weighing an object on Earth, the mass of a distant galaxy cannot be measured directly. Instead, scientists compare its observed light with theoretical models describing how stars of different ages and compositions emit radiation. Suppose two galaxies appear equally bright. One might contain a relatively small number of young massive stars producing enormous amounts of light. The other could contain many older, cooler stars whose combined brightness matches the first. Their luminosities appear similar. Their masses differ substantially. This ambiguity forces astronomers to consider many possibilities simultaneously. Computer models generate millions of potential stellar populations. Researchers compare these virtual galaxies with the observed spectrum until they identify combinations that best match the data. Even then, uncertainties remain. A slightly different history of star formation can alter the estimated mass. Different assumptions about the earliest stars can change the result again. Rather than hiding these uncertainties, astronomers calculate them explicitly. Scientific papers routinely present confidence ranges rather than single definitive numbers. The same careful approach applies to star formation rates. Certain spectral lines become especially bright when massive young stars flood surrounding gas with intense ultraviolet radiation. By measuring the strength of these lines, astronomers estimate how rapidly new stars are forming. Again, interpretation requires caution. Dust can absorb part of the emitted light. Black holes may contribute additional radiation. Gas geometry influences observed brightness. Every measurement carries assumptions that must be tested against alternative explanations. One of the most powerful techniques available to Webb involves chemical analysis. The earliest universe contained almost no heavy elements. Every generation of stars gradually enriched the surrounding gas through stellar winds and supernova explosions. By measuring the abundance of oxygen, carbon, nitrogen, and other elements, astronomers reconstruct a galaxy's evolutionary history. A chemically primitive galaxy suggests relatively little previous star formation. A chemically enriched galaxy implies that multiple generations of stars have already lived and died. This information becomes particularly important when evaluating Webb's most distant observations. Some galaxies appear surprisingly enriched for such early cosmic times. If confirmed, they imply that stellar evolution proceeded remarkably quickly. Not impossibly quickly, simply faster than many previous models anticipated. Even morphology, the visible shape of a galaxy, provides valuable evidence. Early galaxies are often irregular. Some appear clumpy with multiple regions of intense star formation. Others show signs of interactions or mergers. Occasionally, astronomers glimpse structures that hint at surprisingly organized systems beginning to emerge. Every image contributes another clue. Every spectrum adds another sentence to the story. No single observation settles the mystery. Instead, understanding emerges through accumulation. 100 galaxies reveal patterns invisible within 10. 1,000 reveal trends hidden among 100. As Webb continues surveying different regions of the sky, the statistical picture steadily improves. Individual surprises become part of a broader population. This gradual accumulation of evidence explains why astronomy rarely moves in sudden revolutions. Knowledge grows more like a mosaic than a lightning strike. Each observation adds another carefully placed tile. Only after many years does the complete image begin to appear. Today that image remains incomplete. Some pieces fit together beautifully. Others still seem slightly out of place. Rather than forcing them into the existing pattern, astronomers continue gathering more evidence, trusting that nature will eventually reveal how the pieces belong together. And as that evidence has accumulated, several distinct explanations have begun to compete for the same observations. Each is supported by part of the data. Each leaves important questions unanswered. The next step is not to choose the most appealing idea. It is to examine each possibility with equal care. When several explanations remain possible, science enters one of its most interesting phases. From the outside, disagreement can appear unsettling. If experts offer different interpretations of the same observations, it is tempting to assume that no one truly understands what is happening. In reality, the opposite is often true. Carefully reasoned disagreement usually appears only after the evidence has become rich enough to support multiple plausible ideas. The observations are no longer too scarce to study, yet they are not abundant enough to eliminate every alternative. That is precisely where the James Webb Space Telescope has brought astronomy. The observations are real. The distant galaxies are real. The challenge lies in explaining them. One of the leading possibilities is also the most conservative. Perhaps the galaxies themselves are not especially unusual. Perhaps our earlier models simply underestimated how efficiently stars formed during the universe's earliest epochs. This idea requires surprisingly little modification to the standard cosmological picture. Gravity behaves exactly as before. Dark matter continues to guide structure formation. The universe still expands according to well-tested physical laws. Only one ingredient changes. Young galaxies convert gas into stars more rapidly than many simulations previously assumed. This possibility has considerable appeal because star formation is extraordinarily complicated. No computer model can reproduce every turbulent cloud, every magnetic field, every burst of radiation, and every supernova occurring inside billions of galaxies simultaneously. Instead, simulations rely upon carefully tested approximations. If one of those approximations proves slightly incomplete under the extreme conditions of the early universe, galaxies could naturally grow faster without requiring any new physics. Evidence supporting this explanation continues to accumulate. Several Webb observations indicate intense bursts of star formation within compact galaxies. Large quantities of gas appear to have collapsed quickly into dense stellar populations. If these bursts occurred repeatedly across the young universe, they could explain much of the observed brightness. Yet this idea leaves important questions. Can rapid star formation alone account for every unusually luminous galaxy, or does something else contribute additional light? That brings us to another possibility: supermassive black holes. Today, nearly every large galaxy appears to contain one at its center. Some actively consume surrounding gas, producing brilliant regions known as active galactic nuclei. Although black holes themselves emit no light, material falling toward them becomes extremely hot before crossing the event horizon. The resulting radiation can outshine billions of stars. If early galaxies hosted rapidly growing black holes, part of their observed brightness might originate from these energetic central engines, rather than from stars alone. In some Webb observations, this explanation fits remarkably well. Spectra reveal ionized gas consistent with powerful radiation emerging from compact central regions. Other galaxies, however, show little evidence for active nuclei. Black holes may explain part of the puzzle. They do not yet explain all of it. A third idea concerns the stars themselves. The first generation of stars almost certainly differed from those visible today. Modern stars form from gas enriched by billions of years of stellar evolution. Carbon, oxygen, silicon, iron, and many other elements influence how gas cools, fragments, and eventually collapses into stars. The earliest stars formed without those heavier elements. Hydrogen and helium dominated almost completely. Many theoretical models, therefore, predict unusually massive stars during this primordial era. Massive stars shine far more brightly than smaller ones, A galaxy containing many such stars could appear surprisingly luminous even if its total mass remained relatively modest. This possibility has attracted considerable attention because it naturally links several mysteries. It helps explain intense ultraviolet radiation. It may accelerate chemical enrichment. It influences the growth of black holes left behind after massive stars die. Yet one difficulty remains. No confirmed population 3 star has ever been observed directly. The idea rests upon strong theoretical foundations, but direct observational evidence is still being sought. Webb may eventually provide it. For now, the hypothesis remains promising rather than confirmed. Another explanation shifts attention away from galaxies themselves and toward measurement. Estimating stellar masses requires assumptions about how stars emit light. If those assumptions differ slightly under early cosmic conditions, astronomers may unintentionally overestimate galaxy masses. This would reduce much of the apparent tension without altering galaxy formation itself. Several recent studies suggest precisely this possibility. Refined models of stellar populations produce somewhat lower mass estimates for some early galaxies than the first analyses indicated. Importantly, these revisions emerged not because earlier researchers made mistakes, but because improved observations allowed more sophisticated interpretations. Science often progresses through exactly this kind of refinement. Then there are the simulations. Computer models have become extraordinarily powerful. They follow billions of particles representing dark matter. They calculate gravity across enormous volumes of space. They estimate gas cooling star formation, supernova explosions, and black hole growth simultaneously. Yet every simulation remains a simplified representation of reality. Increasing computational resolution often reveals new physical behavior that lower resolution models could not capture. Some researchers therefore argue that current simulations simply require greater detail. As computing power continues improving, galaxies that once appeared unexpectedly massive may emerge naturally within increasingly realistic models. This possibility is difficult to dismiss. Throughout the history of computational science, improved simulations have repeatedly reduced apparent discrepancies between theory and observation. Still another hypothesis considers the role of cosmic environment. The earliest galaxies did not evolve in isolation. Some formed within unusually dense regions where matter accumulated rapidly. These exceptional neighborhoods may have acted like fertile valleys within an otherwise ordinary landscape. If Webb preferentially observes some of these rare environments, the earliest surveys might naturally contain more unusually evolved galaxies than average. Larger observational samples will gradually test this idea. Notice what has happened throughout these competing explanations. Not one requires abandoning the Big Bang. Not one discards general relativity. Not one eliminates dark matter. Instead, each seeks to explain the observations by improving our understanding of complex astrophysical processes already known to exist. This distinction is essential. Popular discussions sometimes present Webb as though it has overturned modern cosmology. Scientific literature tells a quieter story. The standard cosmological model continues explaining an extraordinary range of observations with remarkable success. The question is whether one particularly intricate chapter-early galaxy formation contains additional complexity that previous observations could not reveal. That remains entirely possible. It is equally possible that several explanations contribute simultaneously. Rapid star formation, massive primordial stars, growing black holes, improved stellar population models, refined simulations, dense cosmic environments. Nature rarely chooses only one mechanism when several can operate together. The universe often achieves complexity through the interaction of many simple processes rather than one dramatic event. This realization leads naturally to a deeper question. Suppose one of these ideas or some combination of them is correct. How would that change our broader understanding of cosmic history? Would the early universe merely become a little more efficient? Or would its entire rhythm of evolution begin to look subtly different from the story we have long believed? Suppose for a moment that the earliest galaxies really did grow far more efficiently than astronomers once believed. Not impossibly, not in defiance of physics, simply faster. At first glance, this might seem like a minor adjustment, the sort of refinement that appears regularly in scientific research. After all, theories are updated constantly as new evidence arrives. A parameter changes here, a simulation improves there. The broad picture remains intact, yet sometimes a small change near the beginning of a story quietly reshapes everything that follows. Consider the growth of a forest. If the first trees mature only a few years earlier than expected, they begin producing seeds sooner. Those seeds give rise to another generation, which in turn begins reproducing earlier as well. Over many centuries, that modest head start influences the entire landscape. The forest still grows according to the same biological principles. Its history simply unfolds at a different pace. The earliest galaxies may have played a similar role in the history of the universe. Galaxies are not isolated islands. They constantly influence their surroundings. As stars ignite, they flood nearby space with ultraviolet radiation. Massive stars forge heavier elements inside their cores. Supernova explosions scatter those elements into interstellar clouds, enriching future generations of stars. Black holes release energy that reshapes the gas around them. Galaxies merge, exchange material, and alter one another's evolution. Because of these interactions, the timing of early galaxy formation affects far more than the galaxies themselves. One of the first consequences involves a period known as the epoch of reionization. To understand its importance, we must briefly return to the young universe. After the first atoms formed, the cosmos entered an era often called the cosmic dark ages. Hydrogen filled nearly all of space. There were no stars yet. Illuminating the darkness and only vast clouds of neutral gas slowly responding to gravity. Eventually, the first luminous objects appeared. Their radiation began transforming the universe once again. Energetic ultraviolet photons stripped electrons away from neutral hydrogen atoms, producing ionized hydrogen. This gradual transition spread outward from countless young galaxies until nearly all intergalactic hydrogen became ionized. Astronomers call this process reionization. It represents one of the great turning points in cosmic history. Today, nearly all of the hydrogen between galaxies remains ionized, preserving the signature of that ancient transformation. If the earliest galaxies formed stars more rapidly than expected, reionization may also have progressed more quickly. Instead of a slow, hesitant dawn, the universe may have brightened with surprising efficiency. Webb's observations are beginning to offer important clues. Several distant galaxies appear capable of producing enormous quantities of ultraviolet radiation. Whether enough such galaxies existed to complete reionization remains an active area of research, but each new observation helps refine the picture. The mystery extends beyond light alone. Rapid star formation would also accelerate chemical evolution. The first stars contained almost no elements heavier than helium. When they died, they seeded surrounding gas with carbon, oxygen, magnesium, silicon, and iron. Future generations inherited those materials, making planets and eventually life itself possible. If stellar birth proceeded more vigorously in the infant universe, chemical enrichment would also advance more rapidly. The ingredients required for rocky planets might have become available earlier than previously estimated. This does not imply that life emerged almost immediately after the Big Bang. Many additional conditions are necessary. Stable stars, long-lived planetary systems, suitable environments, complex chemistry. Even so, the cosmic inventory of essential elements may have accumulated sooner than older models suggested. The implications reach even farther. Galaxies grow by attracting matter from their surroundings. Much of that matter first collects within halos of dark matter. These invisible structures formed shortly after tiny density fluctuations began growing under gravity. Ordinary gas then flowed into them, eventually producing stars and galaxies. If early galaxies assembled unusually efficiently, astronomers must ask whether dark matter halos captured gas more effectively than expected. Perhaps gas cooled more rapidly. Perhaps feedback from young stars behaved differently. Perhaps dense cosmic environments supplied a nearly continuous stream of fresh material. None of these possibilities alters the existence of dark matter itself. Instead, they influence how ordinary matter responded to its gravitational framework. The distinction is subtle but important. Dark matter may provide the architecture. Ordinary matter determines much of the visible history. Another fascinating consequence concerns mergers. The early universe was considerably smaller than it is today. Galaxies lay closer together. Interactions occurred far more frequently. Every collision compressed gas triggered star formation and altered galactic structure. If these mergers happened at especially high rates, they could dramatically accelerate the growth of young galaxies. Small systems would rapidly combine into larger ones. Each merger would bring additional gas. Each burst of star formation would enrich surrounding material. Each generation would prepare the next. The resulting evolutionary chain could proceed far more quickly than a simple isolated model might predict. Some of Webb's observations appear consistent with precisely this picture. Several distant galaxies display irregular shapes suggestive of interactions or ongoing mergers. Others contain multiple bright clumps where intense star formation may be occurring simultaneously. Although no single observation proves rapid assembly together, they paint an increasingly dynamic portrait of the young cosmos. Then there are the black holes. If galaxies formed stars efficiently, their most massive stars would die relatively quickly, leaving behind black holes. These remnants could merge accrete gas and gradually evolve into the supermassive black holes observed only a few 100 million years later. In this view, galaxy growth and black hole growth become inseparable chapters of the same story. Each fuels the other. Growing galaxies feed black holes. Active black holes influence galaxies. The relationship continues throughout cosmic history. This interconnected picture has become one of modern astronomy's most exciting frontiers. It suggests that the earliest universe may not have consisted of isolated events unfolding independently. Instead, countless processes evolved together. Gravity gathered matter, stars illuminated darkness, supernovae forged chemistry, black holes reshaped galaxies, radiation transformed intergalactic space. Every process influenced the next. Viewed this way, Webb's discoveries become less surprising. Perhaps the infant universe was never quiet. Perhaps it was extraordinarily productive from the very beginning, not chaotic in the sense of disorder. Chaotic only in the richness of countless physical processes unfolding simultaneously across billions of light years. Yet caution remains essential. This picture, compelling though it may be, is still a hypothesis supported by growing but incomplete evidence. Future observations may strengthen it. They may refine it. Or they may reveal entirely new complexities that no current model anticipates. Science advances precisely because every attractive explanation must ultimately answer to observation. For now, the possibility remains open. If the earliest galaxies truly transformed gas into stars with remarkable efficiency, then the opening chapters of cosmic history were not slower than we imagined. They were simply more vibrant. And if that is true, then the consequences extend beyond individual galaxies. They reach outward into the immense architecture of the universe itself, where galaxies are woven together into structures so vast that even Webb observes only tiny pieces of the greater design. If we could somehow rise far above the Milky Way and continue climbing outward, our familiar galaxy would gradually shrink into a single point of light. Continue farther still and neighbouring galaxies would begin to appear. Beyond them, entire groups of galaxies would emerge, bound together by gravity across millions of light years. Climb even higher, and those groups would connect into clusters. Clusters would join elongated filaments stretching across hundreds of millions of light years, while immense regions almost entirely devoid of galaxies would open between them. Eventually a remarkable pattern would come into view. The universe is not arranged randomly. Instead, galaxies form part of an immense network known as the cosmic web. It is one of the largest structures ever discovered. Yet unlike a spider's web whose silk threads are visible, the framework of the cosmic web is shaped primarily by something that remains invisible: dark matter. Although astronomers cannot observe dark matter directly, its gravitational influence appears throughout the cosmos. Galaxies rotate too quickly for their visible stars alone to hold together. Clusters of galaxies bend light more strongly than ordinary matter can explain. Computer simulations that include dark matter reproduce the large-scale structure of the observable universe with remarkable accuracy. Without dark matter, the universe we inhabit would likely look profoundly different. The galaxies Webb observes were never isolated objects floating through empty space. From their very beginnings, they occupy positions within this larger framework. Understanding that framework changes the way we think about galaxy formation. Imagine rainwater flowing across a mountainside. Water does not spread evenly over every surface. Instead, it naturally follows valleys, gathers within basins, and forms streams that eventually merge into rivers. Matter behaves in a surprisingly similar way across the expanding universe. Tiny differences in density left behind after the Big Bang gradually deepened under gravity. Dark matter accumulated first, creating enormous gravitational valleys. Ordinary gas flowed into these invisible basins, where stars eventually ignited and galaxies began to grow. The cosmic web became the landscape through which matter moved. Some regions remained sparse. Others became extraordinarily rich. This helps explain why galaxies vary so dramatically. A galaxy forming within a dense intersection of filaments may receive a continuous supply of fresh gas flowing inward from multiple directions. Another galaxy growing in a relatively isolated region may experience a much slower evolution. Environment matters. Just as fertile river valleys support different ecosystems than isolated deserts, dense cosmic neighborhoods provide very different conditions from vast intergalactic voids. Webb is beginning to reveal these environments with increasing clarity. Although its field of view is relatively small compared with the enormous scale of the universe, repeated observations across many regions gradually reveal patterns invisible within individual images. Astronomers no longer study only single galaxies. They examine the relationships between galaxies. How close are neighboring systems? Do they align along larger structures? Are intense bursts of star formation more common in certain environments? Do rapidly growing black holes appear preferentially within especially dense regions? These questions extend far beyond individual objects. They concern the architecture of the universe itself. One particularly intriguing possibility is that some of Webb's unexpectedly mature galaxies occupy exceptionally favorable locations within the cosmic web. If matter streamed efficiently along dark matter filaments, certain galaxies may have received enormous quantities of gas early in cosmic history. Instead of relying solely upon the material already surrounding them, they would continuously gather fresh fuel from the larger cosmic environment. This idea resembles a city connected to several major rivers. Trade resources and people arrive more rapidly than they would in an isolated settlement. Growth accelerates. Prosperity follows. The laws governing the city have not changed. Only its position within the larger network has. Astronomers increasingly suspect that location within the cosmic web may have played a similarly important role during the infancy of galaxies. Computer simulations support this possibility. As matter flows through expanding space, dark matter filaments naturally channel gas toward their intersections. These junctions become ideal sites for rapid galaxy growth. Several simulations even predict that the earliest massive galaxies should emerge preferentially within these dense crossroads. Webb's observations provide an opportunity to test those predictions directly. Yet the cosmic web offers more than an explanation for galaxy growth. It also preserves one of cosmology's most beautiful examples of continuity. The tiny fluctuations visible within the cosmic microwave background eventually became the immense filaments stretching across today's observable universe. The difference between those early irregularities and modern superclusters is almost impossible to comprehend. The initial density variations measured only a few parts in 100,000. From such subtle beginnings emerged galaxies containing hundreds of billions of stars. Gravity accomplished this transformation without haste. Over billions of years, small differences became large structures. Tiny advantages accumulated. Minute irregularities expanded into cosmic geography. This remarkable continuity strengthens confidence in the standard cosmological model. The same physical principles explain both the early universe and the large-scale structure visible today. Yet Webb reminds us that continuity does not imply simplicity. Within that broad framework, individual galaxies may still follow surprisingly diverse evolutionary paths. Some remain relatively quiet for billions of years. Others experience repeated bursts of star formation. Some merge frequently. Others evolve in comparative isolation. Some host rapidly growing supermassive black holes. Others do not. The cosmic web provides opportunity. Individual history determines outcome. Another important consequence emerges from this perspective. When astronomers observe one unusually evolved galaxy, they must ask whether it represents a common pattern or a rare exception. This distinction is essential. A handful of extraordinary galaxies cannot overturn a theory describing billions of ordinary ones. Nature often produces remarkable outliers. The tallest mountain does not represent average terrain. The brightest star does not represent typical stars. Likewise, Webb's earliest observations may initially highlight some of the most exceptional galaxies because they are also among the easiest to detect. Fainter, smaller galaxies remain more difficult to observe. As Webb continues surveying larger regions of the sky, astronomers expect the overall population to become increasingly representative. Already that broader picture is emerging. Many early galaxies appear broadly consistent with theoretical expectations. Others remain unexpectedly luminous or massive. The mystery therefore becomes statistical rather than anecdotal. How many unusual galaxies truly exist? How unusual are they? What fraction of the young universe did they represent? These questions require patience. Each new observing campaign adds another portion of the cosmic map. Each additional spectrum refines another measurement. Gradually isolated discoveries become part of a coherent landscape, and within that expanding landscape another surprising realization has begun to emerge. The earliest galaxies may not simply illuminate the history of stars. They may also reveal how the growth of galaxies, the birth of supermassive black holes, and the evolution of the entire cosmic web have been intertwined since almost the very beginning of the universe. For much of the 20th century, astronomers tended to study the universe in separate chapters. Stars belong to stellar astronomy. Galaxies belong to extragalactic astronomy. Black holes occupied their own specialized field. Cosmology focused on the evolution of the universe as a whole. This division was practical. No single researcher could master every branch of an increasingly complex science. Yet nature has never recognized those boundaries. A star does not know that it belongs to stellar physics. A black hole does not distinguish itself from the galaxy surrounding it. The universe operates as one connected system where events separated by millions of light years and billions of years often influence one another in subtle ways. One of Webb's greatest contributions has been to strengthen this interconnected view. The earliest galaxies are no longer seen merely as collections of stars. They are ecosystems. Every component affects the others. Gas flows inward under gravity. Stars ignite within dense clouds. Radiation escapes into surrounding space. Heavy elements accumulate over time. Black holes grow at galactic centers. Each process modifies the environment in which the next unfolds. Understanding any one of them requires understanding all of them. Consider the life of a massive star. Its birth begins quietly inside a collapsing cloud of hydrogen and helium. For millions of years, gravity compresses the gas until nuclear fusion begins deep within the core. The new star shines brilliantly, producing enormous quantities of ultraviolet radiation. This light travels outward, heating nearby gas and influencing neighboring regions where additional stars might otherwise form. Already the star is reshaping its galaxy. Eventually the star reaches the end of its life. Unable to continue supporting itself against gravity, its core collapses. The resulting explosion releases more energy in moments than the sun will emit during its entire lifetime. The supernova scatters newly forged elements across surrounding space. Carbon, oxygen, silicon, iron. Atoms that did not exist before the star was born now become part of the interstellar medium. Future generations of stars inherit these materials. Planets eventually form from them. Every rocky world owes its existence to stars that lived and died long before it appeared. The explosion leaves behind something else as well. Sometimes it is a neutron star. Sometimes it is a black hole. That remnant does not simply disappear into the background. If enough gas continues falling inward, the black hole begins to grow. At first, the process may be relatively modest. Over time, however, repeated accretion and mergers with other black holes gradually increase its mass. Given sufficient fuel, a stellar mass black hole can evolve into something vastly larger. Today, nearly every massive galaxy appears to host a supermassive black hole containing millions, or even billions of solar masses. For many years, astronomers regarded these giant black holes as curious features occupying galactic centers. Increasingly, they appear to be active participants in galactic evolution. As gas spirals toward a growing black hole, friction heats the material to extraordinary temperatures. Before crossing the event horizon, it emits enormous quantities of radiation. Jets of energetic particles may erupt far beyond the galaxy itself. Powerful winds carry matter outward. Far from being passive, the black hole begins influencing the entire galaxy. This process is known as feedback. It represents one of the most important concepts in modern astrophysics. A growing black hole can actually reduce future star formation. By heating surrounding gas or driving it away from the galactic center, it deprives future stars of their raw material. Paradoxically, the object created by previous generations of stars may eventually slow the birth of new ones. The relationship becomes circular. Stars create black holes. Black holes regulate stars. Neither evolves independently. Webb has begun observing this relationship remarkably early in cosmic history. Some of the distant galaxies displaying rapid star formation also show evidence for active central black holes. The implication is profound. The partnership between galaxies and black holes may have begun almost as soon as galaxies themselves appeared. This possibility helps explain another long-standing puzzle. Supermassive black holes seem to have grown extraordinarily quickly. Traditional models often struggle to build billion solar mass black holes within less than 1 billion years after the Big Bang. If early galaxies provided unusually abundant supplies of gas, however, black hole growth could accelerate dramatically. The same dense environments fueling vigorous star formation would naturally nourish growing black holes as well. Once again, seemingly separate mysteries begin converging. Another unexpected connection involves dust. At first thought, dust hardly seems important on cosmic scales. On Earth, dust settles quietly upon forgotten shelves. In galaxies, however, cosmic dust performs an entirely different role. Tiny grains, composed primarily of heavier elements, absorb ultraviolet light and re-radiate it in the infrared. Dust cools gas. It protects molecules from harsh radiation. It encourages new stars to form. Without dust, many of the processes leading to planets would become far less efficient. Yet dust itself requires previous generations of stars. It forms within stellar winds and supernova ejecta. Finding substantial amounts of dust inside very young galaxies, therefore, implies surprisingly rapid stellar evolution. Webb's infrared sensitivity has revealed dusty galaxies existing far earlier than many astronomers anticipated. Again, not impossible. Simply unexpectedly mature. Chemical evolution, star formation, black hole growth, and dust production all appear to have advanced together. The universe was weaving several threads simultaneously. Even the largest structures reflect these connections. Galaxies merge. Their central black holes eventually merge as well. The resulting gravitational interactions alter stellar orbits, reshape galactic structure, and influence future evolution. Over billions of years, repeated mergers gradually transform small irregular systems into the magnificent spiral and elliptical galaxies visible today. No process occurs in isolation. Every chapter prepares the next. This growing recognition has changed the philosophy of astronomy itself. Researchers increasingly combine observations from many different wavelengths. Radio telescopes trace cold hydrogen gas. Infrared observatories reveal dust and ancient galaxies. Visible light telescopes examine stellar populations. X-ray observatories detect energetic black holes. Gravitational wave detectors even observe collisions between compact objects that emit almost no light at all. Each instrument contributes one voice. Together they produce a far richer understanding than any could achieve alone. The James Webb Space Telescope occupies a central place within this expanding orchestra. Its discoveries are valuable not merely because they reveal distant galaxies. They reveal relationships, connections, dependencies. The infant universe begins to appear less like a collection of isolated objects and more like a living network in which every process influences another. This perspective carries an important lesson. Nature often solves complex problems through cooperation rather than simplicity. The earliest galaxies may not have become unexpectedly luminous because of one extraordinary mechanism. Their brilliance may instead reflect many ordinary processes operating together under the unique conditions of the young universe. And if that is true, the next question becomes unavoidable. What new observations are beginning to test these interconnected ideas today? And what fresh surprises is the James Webb Space Telescope continuing to uncover, as its exploration of the ancient cosmos has only just begun? When the James Webb Space Telescope released its first scientific images, they were celebrated around the world for their extraordinary beauty. Towering columns of gas glowed in delicate shades of gold and blue. Spiral galaxies stretched across deep fields in astonishing detail. Stellar nurseries appeared with a clarity that had never before been possible. Yet for astronomers, the most important discoveries were often hidden in places that looked almost empty. A tiny red point of light, a faint spectrum spread across a detector, a subtle chemical signature buried within a handful of photons. These were the observations capable of reshaping our understanding of the earliest universe. What makes Webb especially remarkable is that it is no longer producing isolated discoveries. It is steadily building a growing archive of evidence. Every observing cycle adds hundreds of new targets. Every spectrum improves a statistical picture. Every confirmed redshift helps astronomers distinguish genuine patterns from rare exceptions. This gradual accumulation is transforming early excitement into careful scientific understanding. One important development has been the increasing number of spectroscopically confirmed galaxies from the universe's first few 100 million years. During Webb's earliest months, many distant galaxy candidates were identified using photometric techniques. Those initial estimates were intentionally cautious, serving as invitations for deeper investigation rather than final conclusions. Since then, many of those candidates have been revisited. Some proved to be exactly as distant as hoped. Others turned out to belong to later periods of cosmic history. Far from being disappointing, these refinements strengthened confidence in the remaining measurements. Every confirmed galaxy became another reliable point on humanity's map of the early cosmos. As that map expanded, another pattern emerged. The earliest galaxies displayed remarkable diversity. Some are surprisingly compact, containing intense bursts of star formation within relatively small volumes. Others appear more extended, suggesting that gas had already spread across larger regions than some theoretical models anticipated. Some seem dominated by young brilliant stars. Others show evidence that several generations of stars may already have enriched their surrounding gas. Rather than revealing one universal type of primordial galaxy, Webb is uncovering an entire population with varied histories. That diversity itself carries important information. It suggests that galaxy evolution began branching into different pathways remarkably early. Even while the universe was still young, environment mergers, gas supply, and local conditions were already producing distinct evolutionary outcomes. Another area of rapid progress involves chemical composition. Webb's spectroscopic instruments continue detecting emission lines from oxygen, carbon, neon, and other elements inside galaxies that existed astonishingly early in cosmic history. These measurements allow astronomers to estimate how quickly stellar evolution enriched the young universe. Some galaxies appear chemically primitive, closely matching theoretical expectations. Others seem unexpectedly enriched, implying vigorous cycles of star birth and stellar death occurring within surprisingly short periods. Again, the observations do not overturn existing theory. Instead, they encourage refinements in how quickly those processes unfolded. At the same time, Webb has begun revealing active galactic nuclei in increasingly distant galaxies. These brilliant central regions indicate rapidly growing black holes. Each newly discovered example helps researchers estimate how common such objects were during the universe's infancy. If supermassive black holes became widespread earlier than expected, their influence upon surrounding galaxies may also have begun earlier. Understanding this relationship has become one of the central goals of modern astrophysics. Yet Webb is not working alone. One of the most exciting aspects of contemporary astronomy is the cooperation between many different observatories. The James Webb Space Telescope provides exquisite infrared observations. Ground-based telescopes equipped with enormous mirrors perform complementary spectroscopy at visible and near-infrared wavelengths. Radio observatories trace cold gas that cannot be seen by optical instruments. X-ray telescopes reveal energetic black holes hidden within dusty galaxies. Each observatory contributes a different piece of the puzzle. Sometimes one telescope discovers an intriguing galaxy, another measures its chemical composition, a third detects surrounding gas. Together they produce a far richer portrait than any single instrument could achieve. Computer simulations have evolved alongside these observations. Modern cosmological simulations now incorporate increasingly sophisticated models of star formation, black hole, feedback, magnetic fields, chemical enrichment, and gas dynamics. Instead of merely reproducing the large-scale distribution of galaxies, they attempt to capture the intricate physical processes unfolding inside individual systems. As new Webb data become available, theorists compare real galaxies with simulated ones. When differences appear, the simulation are revised. Sometimes cooling rates are adjusted. Sometimes feedback mechanisms are refined. Sometimes entirely new physical interactions are incorporated into the models. This continuous dialogue between observation and theory represents one of science's greatest strengths. Neither exist independently. Observations challenge simulations. Simulations guide future observations. Each improves the other. Artificial intelligence has also begun playing an increasingly important role. Modern surveys generate enormous quantities of data. Millions of galaxies must be identified, classified, and analyzed. Machine learning algorithms help recognize subtle patterns that would require enormous amounts of human effort to detect manually. Importantly, these systems do not replace astronomers. Instead, they serve as powerful assistants, allowing researchers to focus their attention on the most scientifically interesting objects. As Webb's archive continues growing, such tools become increasingly valuable. Perhaps the most remarkable realization emerging from recent observations is not that the universe appears stranger than expected. It is that the earliest cosmos already possessed astonishing richness. Within only a few 100 million years, galaxies were interacting. Stars were transforming chemistry. Black holes were growing. Dust was forming. Radiation was reshaping intergalactic space. Processes that continue today had already begun weaving together an intricate cosmic tapestry. The infant universe was not an empty stage waiting for history to begin. History had already begun. Even so many observations remain tantalizing rather than definitive. Several intriguing galaxies still await more detailed spectroscopy. Additional observing campaigns will improve measurements of stellar mass and chemical abundance. Future surveys will expand beyond today's relatively small samples, revealing whether unusual galaxies were common or exceptionally rare. The story continues to evolve with every new observing cycle. Perhaps that is the most beautiful aspect of Webb's mission. Unlike many famous scientific discoveries, its greatest achievements are not confined to the past. The telescope continues observing tonight. Ancient photons continue arriving. New spectra continue being recorded. Somewhere within those faint streams of infrared light may already exist clues to questions astronomers have not yet thought to ask. And despite all that has been learned, the deeper we look into the early universe, the more clearly one truth emerges. Our knowledge has expanded enormously. Our uncertainty has expanded with it. For every mystery Webb has helped resolve, it has revealed several more waiting just beyond the edge of our present understanding. There is a quiet temptation in every scientific discovery. Once a new observation appears convincing, it is natural to assume that the remaining questions are merely details waiting to be filled in. History, however, tells a different story. Every major advance in astronomy has expanded not only humanity's knowledge, but also the boundaries of its ignorance. The James Webb Space Telescope is following that same pattern. Its observations have answered questions that astronomers debated for decades. We now know that galaxies existed surprisingly early in cosmic history. We know that some were already actively forming stars. We know that black holes were growing while the universe was still remarkably young. We know that chemical enrichment began rapidly after the first generations of stars. Yet each answer opens another question. Perhaps the most fundamental uncertainty concerns the first stars themselves. Astronomers have given them a name, population 3 stars. According to modern theory, these stars formed from nearly pure hydrogen and helium before heavier elements had been created inside stellar cores. Without carbon, oxygen, silicon, or iron to help cool collapsing clouds of gas, These first stars may have formed under conditions unlike anything that exists today. Many simulations suggest they were extraordinarily massive. Some may have contained dozens or even hundreds of times the mass of the Sun. If so, they would have burned intensely, lived briefly, and died in spectacular explosions that permanently altered the chemistry of the universe. And yet, despite decades of searching, no population 3 star has been confirmed directly. Their existence is strongly supported by theory. Indirect evidence continues to accumulate, but the stars themselves remain unseen. Perhaps they were too short-lived. Perhaps they formed only in environments that are exceptionally difficult to observe. Or perhaps some details of their formation differ from current predictions. For now, they remain one of astronomy's most compelling missing chapters. Another uncertainty involves the earliest black holes. Every large galaxy observed nearby appears to contain a supermassive black hole. Some possess masses equivalent to billions of suns. The question is not whether these objects exist. The question is how they became so enormous so quickly. There are several possibilities. One idea begins with the deaths of the first massive stars. Each collapse leaves behind a relatively small black hole that gradually grows through accretion and repeated mergers. Given enough time, these seeds eventually become supermassive. Another possibility proposes much larger beginnings. Instead of forming from individual stars, some enormous clouds of gas may have collapsed directly into black holes containing tens of thousands or even hundreds of thousands of solar masses. Such objects would begin life with a significant advantage. They would require much less subsequent growth to explain Webb's observations. Neither scenario has yet been confirmed. Both remain active areas of research. Future observations may distinguish between them, or nature may reveal that both pathways occur under different conditions. The uncertainty extends beyond individual objects. Astronomers also continue debating the efficiency of early star formation. How much gas became stars? How rapidly did this happen? How strongly did stellar winds and supernova explosions regulate future star formation? These questions seem straightforward, but they involve extraordinarily complicated physics. Gas behaves turbulently. Magnetic fields influence its motion. Radiation heats surrounding clouds. Gravity compresses them. Every process interacts with every other. Even the most sophisticated simulations cannot calculate every detail directly. Approximations remain unavoidable. Webb is helping refine those approximations, but complete certainty remains distant. Then there is dark matter. Throughout this documentary, dark matter has quietly shaped almost every chapter. Its gravitational influence appears essential for explaining the formation of galaxies and the structure of the cosmic web. Yet its true nature remains unknown. Astronomers observe its effects. Physicists continue searching for the particles that may compose it. Despite decades of experiments, no direct detection has yet succeeded. This absence does not eliminate dark matter. Multiple independent observations still support its existence remarkably well. But one profound question remains unanswered. What is it? Equally mysterious is dark energy. Although it plays a smaller role during the era of the earliest galaxies, dark energy now dominates the large-scale evolution of the universe by driving accelerated cosmic expansion. Its physical origin remains one of the deepest mysteries in all of science. The early galaxies observed by Webb are helping constrain cosmological models, yet they have not solved this larger puzzle. Measurement itself introduces additional uncertainty. Even with Webb's extraordinary capabilities, astronomers observe only a tiny fraction of the observable universe. Its deepest fields cover remarkably small patches of sky. Those regions may or may not represent average cosmic environments. Some could contain unusually dense concentrations of galaxies. Others might sample comparatively empty space. Expanding observational coverage remains essential before broad statistical conclusions can be drawn. Cosmic variance, as astronomers call it, reminds researchers to remain cautious when interpreting limited samples. The earliest galaxies may appear more or less common depending upon where we happen to look. Time also complicates interpretation. Every distant galaxy is observed only once. Unlike nearby objects that can be monitored over decades, ancient galaxies provide single snapshots frozen in cosmic history. Astronomers must reconstruct entire evolutionary histories from these isolated moments. It is a remarkable achievement. It is also an unavoidable limitation. The universe rarely allows repeated experiments. Instead, it presents countless unique examples from which broader patterns must be inferred. Perhaps the greatest uncertainty of all concerns questions not yet imagined. History repeatedly shows that new instruments reveal phenomena no one expected. Galileo didn't build his telescope expecting to discover moons around Jupiter. Edwin Hubble did not begin by searching for an expanding universe. The discovery of the cosmic microwave background occurred almost accidentally. The James Webb Space Telescope may likewise uncover entirely new questions before its mission concludes. Already observations continue extending farther into cosmic history than many researchers anticipated. Each observing cycle increases sensitivity. Each improved analysis extracts additional information from existing data. The frontier keeps moving, and every time that frontier advances, certainty retreats just enough to reveal another unexplored horizon. This is not a weakness of science. It is its greatest strength. Knowledge does not end with answers. It grows through better questions. The universe has never promised to be simple. It has only promised to be consistent. Our task is to keep learning its language one observation at a time. And as Webb continues reading the oldest surviving light in existence, astronomers find themselves approaching the true edge of contemporary knowledge, where observation becomes increasingly difficult. Theory increasingly subtle, and every new photon may carry evidence capable of changing how humanity understands its place within the cosmos. Every map has an edge. For ancient sailors, the edge marked the limit of familiar coastlines. Beyond it lay oceans that had not yet been charted. For 19th century explorers, the blank spaces appeared deep within continents, whose mountains, rivers, and forests remained largely unknown. Modern astronomy possesses its own frontier. It does not lie at the edge of the observable universe, but at the boundary between what light can reveal and what current science can confidently explain. The James Webb Space Telescope has carried humanity closer to that boundary than any previous observatory. Yet the closer we approach, the more difficult every step becomes. This difficulty begins with light itself. The oldest photons reaching Webb have spent more than 13 billion years travelling across expanding space. During that immense journey, their wavelengths have stretched into the infrared. Their energy has diminished. Their numbers are extraordinarily small. By the time they arrive at the telescope, they're among the faintest signals ever measured by human instruments. Detecting them requires extraordinary patience. Some observations continue for many hours. Others accumulate light over multiple observing sessions. Every additional photon slightly improves the final image. Every increase in observing time allows astronomers to glimpse objects that were previously hidden within statistical noise. The challenge resembles listening for a whisper carried across an entire continent. Even then, collecting light is only the first obstacle. Interpreting that light is equally demanding. A distant galaxy may appear as only a few blurred pixels. Its spectrum may contain faint emission lines barely distinguishable from background noise. Determining its distance, chemical composition, and stellar population requires careful statistical analysis rather than simple visual inspection. Astronomers must constantly distinguish genuine signals from instrumental artifacts, random fluctuations, and competing interpretations. This is why confidence in science grows gradually. Not because researchers hesitate, because evidence deserves time. Theoretical challenges become equally demanding. Galaxy formation is governed by gravity, hydrodynamics, magnetic fields, radiation, turbulence, chemistry, stellar evolution, black hole physics, and cosmic expansion simultaneously. Each process influences the others. Changing one parameter can produce consequences throughout an entire simulation. Modern supercomputers perform calculations involving billions of particles and enormous volumes of space. Yet even these machines cannot resolve every cloud of gas, every magnetic filament, or every individual star. Choices must be made. Small-scale physics is represented through carefully tested approximations. These approximations have become increasingly sophisticated over time, but they remain approximations nonetheless. Webb is now testing them under conditions that no previous observations could reach. Sometimes the simulation perform remarkably well. Sometimes they require adjustment. That ongoing dialogue between theory and observation defines the frontier of cosmology. Another limitation arises from time. The observable universe offers only one history. Physicists often test ideas by repeating experiments under controlled conditions. Astronomers cannot. There was only one Big Bang, only one sequence of cosmic evolution, only one observable universe. Researchers therefore rely upon comparison rather than repetition. Millions of galaxies become millions of natural experiments. Patterns emerge statistically rather than experimentally. This makes astronomy both powerful and humbling. Nature has already performed the experiment. Humanity can only observe the outcome. The frontier also reveals itself through technology. Although Webb represents one of the most advanced scientific instruments ever constructed, it cannot observe every wavelength equally well. Some questions require radio telescopes, others require X-ray observatories, still others may eventually require instruments that have not yet been built. Every telescope sees only part of reality. Together they create a more complete picture. The same is true of gravitational wave astronomy. Only recently have detectors become sensitive enough to measure tiny distortions of space-time produced by merging black holes and neutron stars. These observations provide information entirely different from light. Future gravitational wave observatories may detect events occurring during the earliest stages of galaxy formation, adding another dimension to our understanding of cosmic history. Neutrino astronomy offers another frontier. These nearly massless particles pass through ordinary matter almost without interaction. They emerge from violent astrophysical events, carrying information that photons sometimes cannot provide. One day, neutrino observations may help illuminate environments hidden even from Webb's infrared instruments. Perhaps the greatest frontier, however, is conceptual. Every successful scientific theory possesses a domain within which it performs extraordinarily well. Newton's laws describe everyday motion with remarkable accuracy. General relativity explains gravity across planets, stars, and galaxies. Quantum mechanics governs the microscopic world with astonishing precision. Yet physicists still seek a deeper framework capable of uniting gravity with quantum theory. The earliest universe lies close to the region where such a theory may eventually become necessary. Webb does not observe the instant of the Big Bang itself. Its view begins hundreds of millions of years later. Even so, every improvement in our understanding of early galaxies constrains theories describing what came before. Small refinements ripple backward through cosmic history. This is why seemingly modest observations matter so much. A revised estimate of stellar mass, a newly measured chemical abundance, an additional confirmed galaxy at extreme redshift. Each piece narrows the range of possibilities. Each removes some theoretical paths while strengthening others. Scientific frontiers rarely advance through dramatic leaps. They progress through countless careful measurements accumulating over many years. There is another reason the frontier remains elusive. The universe often refuses to organize itself according to human categories. Galaxies are not merely collections of stars. Black holes are not merely gravitational objects. Dark matter is not merely invisible mass. Every phenomenon participates in a larger network of physical relationships. Understanding one often requires understanding many others simultaneously. Webb has made this increasingly clear. The earliest galaxies cannot be understood without considering dark matter. Dark matter cannot be fully appreciated without examining the cosmic web. The cosmic web influences mergers. Mergers affect black holes. Black holes regulate star formation. Star formation creates the chemistry from which planets eventually arise. Every thread connects to another. This realization transforms the frontier from a single boundary into an intricate landscape. Some regions are well explored. Others remain almost untouched. Between them stretches an ever-changing border where observation meets uncertainty. It is here that astronomy now stands. Not at the end of discovery, not at the completion of a grand theory, but at the beginning of a new era, in which each additional observation extends humanity's vision a little farther into the ancient darkness. And as that frontier slowly advances, an even larger question begins to emerge. If our understanding of the first galaxies continues to evolve, what does that ultimately tell us about the history of the universe itself, and about our own place within that immense unfolding story? When people speak about the history of the universe, It is often tempting to think in terms of fixed milestones. The Big Bang happened, the first stars formed, galaxies appeared, planets emerged, life eventually arose. Presented in this way, cosmic history can sound almost inevitable, as though every chapter unfolded exactly as it had to. The deeper astronomy looks, however, the more nuanced that picture becomes. The broad sequence remains remarkably well supported. What changes are the details, and sometimes those details influence how we understand the entire story. The James Webb Space Telescope has reminded us that the universe is not simply a collection of objects moving through space. It is a history unfolding through time. Every galaxy is both a destination and a consequence. Its appearance reflects billions of years of physical processes that began long before the galaxy itself existed. If some of the earliest galaxies grew more rapidly than expected, then the opening tempo of cosmic evolution may have been subtly different from what earlier generations of astronomers imagined. The melody remains recognizable. The rhythm becomes richer. This distinction is important because cosmology has never been about memorizing isolated facts. Its goal is to explain how simple beginnings gave rise to extraordinary complexity. At first, the universe contained almost nothing beyond hydrogen, helium, radiation, dark matter, and expanding space. From those remarkably simple ingredients emerged galaxies, stars, planets, oceans, atmospheres, chemistry, biology, and eventually conscious observers capable of asking where they came from. Few scientific questions are more profound. How does complexity arise from simplicity? Gravity provides part of the answer. It gathers matter into ever larger structures. Stars provide another. They manufacture the chemical elements needed for future generations of planets. Galaxies create environments where billions of stars evolve together, enriching one another across immense spans of time. Each level of organization prepares the next. The earliest galaxies therefore occupy a uniquely important position. They represent one of the first occasions when the universe began transforming raw material into lasting structure. Understanding how efficiently they accomplished that task affects every chapter that followed. Consider the elements inside the human body: the calcium in bones, the oxygen carried by blood, the carbon forming every cell, the iron helping red blood cells transport oxygen. None existed immediately after the Big Bang. Everyone was forged inside stars that lived, evolved, and died. Those stars belong to galaxies. The pace at which galaxies form therefore influenced the pace at which cosmic chemistry advanced. In this sense, Webb's observations are not merely about distant objects. They concern the earliest origins of the material from which every living organism is ultimately built. That realization quietly reshapes perspective. The galaxies appearing as tiny red points within Webb's images are not unrelated to us. They are distant ancestors within the history of matter itself. Their stars enrich the universe. Later generations inherited that enrichment. Still later came planetary systems. Eventually one of those systems produced Earth. The chain is long, yet it is continuous. Another implication concerns predictability. For many years, computer simulations have demonstrated remarkable success in reproducing the large-scale structure of the universe. The cosmic web, galaxy clusters, dark matter filaments. These achievements remain among the great triumphs of modern cosmology. Yet Webb reminds us that predicting detailed galactic evolution is considerably more difficult. Small differences in gas cooling, minor variations in star formation efficiency, subtle changes in feedback from black holes. Each can alter the appearance of galaxies over hundreds of millions of years. Nature is deterministic in its physical laws. Its outcomes are nonetheless wonderfully diverse. This diversity carries an important philosophical lesson. Scientific understanding does not require every detail to be perfectly predictable. Meteorologists understand atmospheric physics, yet they cannot predict every cloud months in advance. Biologists understand evolution without predicting every species that will emerge. Likewise, cosmologists may understand the governing principles of galaxy formation, while individual galaxies still follow many possible evolutionary pathways. The universe contains both order and variety. Webb has also encouraged astronomers to think more carefully about timescales. Human intuition struggles with billions of years. Even 100 million years seems unimaginably long. Against cosmic history, however, 100 million years represents only a brief interval. If galaxies reached maturity 50 or 100 million years earlier than expected, that difference may seem small compared with the age of the universe. Yet during its earliest epoch, such intervals represented a substantial fraction of cosmic history. Tiny adjustments near the beginning can influence everything that follows. The same principle appears throughout nature. A river's course depends sensitively upon its earliest channels. A forest's future reflects the timing of its first growth. The opening conditions often matter disproportionately. Perhaps the most enduring implication of Webb's discoveries concerns the nature of scientific confidence itself. Popular discussions sometimes portray science as a collection of permanent answers. Reality is more elegant. Science is a method for reducing uncertainty. Some conclusions become extraordinarily reliable because countless independent observations support them. The expansion of the universe, the existence of galaxies, the cosmic microwave background, the synthesis of heavy elements inside stars. Other conclusions remain provisional because evidence continues evolving. Exactly how rapidly the earliest galaxies formed, how the first stars differed from later generations, how supermassive black holes achieved their enormous masses, these questions remain open. There is no contradiction between confidence and curiosity. The strongest scientific theories are precisely those capable of absorbing new evidence without losing their explanatory power. Modern cosmology has repeatedly demonstrated that resilience. Webb has not diminished its achievements. It has expanded its responsibilities. The theory must now explain an even richer universe than previous generations were able to observe. That challenge is not a crisis. It is an opportunity. Every additional observation allows astronomers to refine the remarkable narrative describing how the observable universe evolved from almost perfect simplicity into astonishing complexity. And perhaps the greatest consequence of all is this. The farther we look into space, the more clearly we discover that humanity did not appear at the end of an isolated story. We emerge from a history that began billions of years before the Earth itself existed. The earliest galaxies were among its first enduring chapters. Understanding them means understanding the opening pages of our own cosmic origin. Yet the story is still unfinished. Because even as Webb continues revealing the ancient past, astronomers are already preparing instruments that may look still farther back, carrying this search into chapters of cosmic history that remain entirely beyond today's horizon. Every generation believes it has reached the edge of discovery. Then a new instrument is built, a new window opens, and the horizon quietly moves farther away. The James Webb Space Telescope represents one of those moments. Its observations have already transformed our view of the early universe, yet Webb was never intended to provide the final word on cosmic history. Like every great observatory before it, its greatest achievement may be the questions it leaves for those that follow. Astronomy has always advanced in this way. Each telescope inherits the mysteries of its predecessor while uncovering mysteries of its own. Galileo's small refracting telescope revealed moons circling Jupiter and mountains upon the moon. Centuries later, giant reflecting telescopes mapped distant galaxies. The Hubble Space Telescope showed that galaxies filled even the darkest regions of the sky. Webb has carried us farther still, revealing light emitted when the universe was only a few 100 million years old. Yet even that remarkable accomplishment leaves much of cosmic history unexplored. The earliest stars almost certainly formed before many of the galaxies Webb now observes. The first black hole seeds may have appeared earlier still. Between the release of the cosmic microwave background and the birth of the first luminous objects stretches a vast interval, known as the Cosmic Dark Ages. Much of that era remains hidden. No ordinary visible light survives from those times because there were not yet stars to produce it. Astronomers therefore seek entirely different ways of exploring that ancient darkness. One promising approach involves radio astronomy. Neutral hydrogen naturally emits radiation at a wavelength of 21 centimeters. As the universe expanded, that signal stretched dramatically, reaching radio wavelengths detectable by specialized instruments. Future observatories hope to map this faint glow across enormous volumes of space. Rather than observing individual galaxies, they will trace the distribution of hydrogen itself. Such observations could reveal how the first stars gradually transformed the cosmic dark ages into the luminous universe we know today. Another frontier lies beneath the ground rather than above it. Across different continents, physicists are constructing increasingly sensitive detectors designed to search directly for dark matter. If the particles responsible for dark matter are eventually identified, astronomers will gain an entirely new understanding of the invisible framework guiding galaxy formation. Webb observes the consequences of dark matter. Future experiments may uncover its true identity. Gravitational wave astronomy is also entering an extraordinary period. The first detections of merging black holes demonstrated that space-time itself can carry information across the cosmos. Future space-based observatories will extend this capability dramatically. Instead of observing only relatively nearby mergers, they may detect collisions involving black holes from much earlier periods of cosmic history. Such measurements could reveal how rapidly black holes assembled during the universe's infancy. Information that today must be inferred indirectly may one day be measured directly. Computer simulations will continue evolving alongside these observational advances. Every increase in computing power allows researchers to represent smaller physical scales while simultaneously modeling larger cosmic volumes. Processes that once required simplified approximations gradually become explicit calculations. Magnetic fields can be followed more accurately. Gas turbulence can be modeled in greater detail. Black hole feedback becomes increasingly realistic. Each improvement narrows the gap between theoretical predictions and observational evidence. Artificial intelligence will almost certainly play an expanding role as well. Future observatories will generate data on a scale impossible for individual researchers to examine manually. Machine learning systems will identify unusual galaxies, classify spectra, recognize subtle patterns, and help prioritize the most scientifically valuable targets. Importantly, these systems will not replace scientific reasoning. They will extend human attention, allowing astronomers to ask deeper questions than ever before. Perhaps the most exciting possibility is one that cannot yet be predicted. History repeatedly reminds us that transformative discoveries often emerge unexpectedly. The cosmic microwave background was not discovered because researchers were searching specifically for it. Pulsars were initially so mysterious that their discoverers jokingly labeled them little green men. The accelerating expansion of the universe emerged while astronomers were measuring distant supernovae for an entirely different purpose. Nature frequently rewards careful observation with surprises. Webb itself has already demonstrated this principle. It was expected to discover ancient galaxies. It was not expected to stimulate such vigorous discussion about how rapidly some of them formed. Future instruments may reveal phenomena that today exist only beyond imagination. Perhaps new classes of galaxies, perhaps entirely different modes of star formation, perhaps unexpected properties of dark matter, perhaps something that no current theory anticipates at all. The history of science encourages humility precisely because the universe has repeatedly proven richer than human expectation. Even so, it is important to distinguish informed speculation from established knowledge. Astronomers can make careful predictions based upon existing evidence. They cannot claim certainty about observations that have not yet been made. This distinction preserves the integrity of scientific inquiry. Curiosity drives exploration. Evidence determines conclusions. As we look farther into the future, another realization slowly emerges. The questions surrounding the earliest galaxies are unlikely ever to be answered by one telescope alone. Instead, they will require a community of observatories operating across every wavelength of light, combined with gravitational wave detectors, particle physics experiments, advanced simulations, and generations of researchers building upon one another's work. Scientific discovery resembles the construction of a cathedral. No single craftsperson completes the entire structure. Each contributes one carefully shaped stone. Future astronomers will inherit the foundation Webb has established. They will test its conclusions, refine its measurements, challenge its assumptions, expand its reach. The telescope orbiting quietly around the Sun today is therefore more than a scientific instrument. It is the beginning of a conversation that may continue for centuries. Long after Webb itself has completed its mission, the questions it helped uncover will remain. And somewhere beyond the frontier, it has revealed ancient light is still travelling toward us, carrying information from chapters of cosmic history that no human being has yet read. At the beginning of this journey, we started with an idea that seemed almost self-evident. The early universe we believed must have been simple. Galaxies, like living organisms, would begin small. They would gather matter, slowly experience gradual growth, and only after immense spans of time would they develop into the magnificent structures that fill today's cosmos. It was a reasonable expectation. It emerged from decades of careful observation, successful theory, and increasingly sophisticated simulations. It was never an arbitrary assumption. It represented the best explanation that generations of astronomers could build from the evidence available to them. Then humanity looked farther than it ever had before. The James Webb Space Telescope did not set out to overturn this picture. It set out to examine it. And that distinction has shaped everything we have learned. Throughout this documentary, one theme has appeared again and again. The universe has not contradicted itself. It has become more detailed. That difference may seem subtle, yet it lies at the heart of scientific progress. When Webb revealed galaxies shining only a few 100 million years after the Big Bang, the immediate question was not whether the laws of physics had failed. It was whether our understanding of those laws under the unique conditions of the infant universe was complete. As more observations accumulated, the picture grew steadily richer. Some galaxies once thought impossibly distant turned out to be somewhat closer. Some initial mass estimates were revised downward. Other galaxies remained genuinely remarkable. Their rapid star formation, vigorous black hole activity, and surprisingly mature chemical composition continued challenging astronomers to refine existing models. The mystery evolved. Instead of asking whether these galaxies should exist, researchers began asking how they could have formed so efficiently while remaining consistent with everything else we know about the cosmos. That question has led us through many interconnected ideas. The invisible framework of dark matter guiding cosmic structure, the first generations of stars enriching the universe with heavier elements, black holes growing alongside their host galaxies, radiation transforming the intergalactic medium, the immense filaments of the cosmic web directing the flow of matter across unimaginable distances. Viewed separately, each process is fascinating. Viewed together, they reveal something deeper. The universe has always been a system of relationships. No galaxy forms alone. No star evolves in isolation. No black hole grows without influencing its surroundings. Every event participates in a network extending across both space and time. Perhaps this is the most important lesson Webb has offered. Complexity did not suddenly appear after billions of years. Its foundations were present astonishingly early. Even while the universe was still young, gravity, chemistry, radiation, and cosmic expansion were already interacting in ways that produced extraordinary diversity. The first galaxies were not identical. Some evolved rapidly. Others developed more gradually. Some became brilliant centers of star formation. Others remained comparatively modest. The opening chapters of cosmic history are already rich with variation. That realization changes how we think about the word young. Human intuition often associates youth with simplicity. A young forest contains only saplings. A young civilization possesses only its earliest settlements. A young galaxy, however, may already be the product of millions of years of intense physical activity. By the time its light reaches Webb, countless stars may already have been born and died. Chemical elements may already have spread through surrounding gas. Black holes may already have begun reshaping the galaxy from within. Cosmic youth does not necessarily imply cosmic immaturity. The difference matters. It reminds us that time in astronomy operates on scales unlike anything encountered in everyday life. Hundreds of millions of years represent an almost incomprehensible duration by human standards. Within that interval, gravity can transform faint fluctuations into galaxies. Stars can manufacture the ingredients of planets. Entire regions of the universe can change character. Another theme has quietly accompanied us throughout this journey: patience. Gravity is patient. Light is patient. Science is patient. The photons reaching Webb today have travelled for more than 13 billion years without interruption. Astronomers spend years planning observations, months analysing spectra, and decades refining theories. Knowledge advances not through haste but through persistence. That patience has allowed humanity to reconstruct a story spanning nearly the entire age of the observable universe. Not perfectly, not completely, but with astonishing depth. Perhaps that is why the discoveries of the James Webb Space Telescope feel so meaningful. They do not merely provide new facts. They remind us that understanding is always provisional. Every answer becomes the beginning of another question. Every successful theory invites more precise testing. Every improved instrument reveals phenomena once hidden beyond the limits of observation. The universe has not become stranger because Webb looked deeper. It has become clearer, and clarity often reveals complexity that distance once concealed. The assumption with which we began has therefore changed. The early universe was never simply empty space waiting for galaxies to appear, nor was it a tranquil place where cosmic history unfolded at an unhurried pace. It was dynamic, creative, governed by elegant physical laws operating across extraordinary scales of time and distance. Those laws remain consistent. Our understanding of how they shaped the first galaxies continues to grow. In that sense, the greatest discovery is not that some galaxies appeared earlier than expected. It is that the universe continues rewarding careful observation with deeper coherence rather than greater confusion. Every new observation does not erase what came before. It places previous knowledge within a broader and more beautiful context. And yet even after everything Webb has revealed, one final thought remains waiting beyond the edge of certainty. The farther we travel into the ancient past, the more closely we approach the beginning of a story whose first pages are still incomplete. Those missing pages continue drifting toward us as faint streams of ancient light carrying answers that have spent almost the entire lifetime of the universe on their way to Earth. For thousands of years, humanity has looked upward with the same quiet question. What is this place in which we find ourselves? Every civilization answered differently. Some imagined celestial rivers flowing across the heavens. Others saw divine beings arranging the stars into patterns of meaning. Later generations discovered planets orbiting the sun galaxies beyond the Milky Way, and an expanding universe whose history stretched billions of years beyond human memory. Each answer felt immense, yet every answer eventually became the beginning of another question. That quiet rhythm has never changed. Throughout this journey, we've followed light farther than any previous generation could have imagined. We've traced photons that began their voyage long before Earth existed. We have watched galaxies emerge from darkness while the universe itself was still remarkably young. We have seen gravity patiently gather matter into the first enduring structures. Stars transform simple elements into richer chemistry, and black holes grow alongside the galaxies that surrounded them. Piece by piece, the early cosmos has become less distant, not because it has moved closer, because understanding has. The James Webb Space Telescope has allowed humanity to read chapters of cosmic history that were hidden for almost the entire existence of our species. Those ancient photons travelled uninterrupted across expanding space, surviving billions of years simply to arrive at a mirror quietly orbiting the sun beside our small blue world. There is something profoundly gentle about that thought. The universe has never hurried its story. The light we observe today left its galaxies before the Milky Way acquired much of its present form. It crossed regions of space that did not yet contain many of the stars now visible in our night sky. While continents shifted, oceans opened and closed, species appeared and disappeared. Civilizations rose and faded, those same photons continued their silent journey. Only now have they reached observers capable of asking what they mean. Perhaps that is one of astronomy's most remarkable gifts. It stretches our sense of time. Human history often feels immense because it spans thousands of years. Geological history extends that perspective into millions. Cosmology expands it again, inviting us to think naturally in billions of years. Against such scales, individual lives become brief. Yet they also become precious, for within those brief lives exists the extraordinary ability to understand events unimaginably older than ourselves. The atoms inside every human body were forged in stars that no longer exist. The oxygen we breathe, the calcium within our bones, the iron carried through our blood, all began their journeys inside ancient stellar furnaces. Those stars belong to galaxies that inherited material from even earlier generations. Every living organism is therefore connected to a chain of cosmic history, extending almost to the beginning of the observable universe. We are not separate from that history. We are one of its most recent expressions. The discoveries of Webb deepen that connection. The galaxies appearing as tiny crimson points in its images are not merely distant curiosities. They represent some of the earliest places where the universe began building lasting complexity. Within them, gravity and light gas and chemistry, order and chance combined to shape everything that followed. Understanding those galaxies is in a very real sense part of understanding ourselves. And yet after all we have explored, the central mystery remains beautifully unfinished. Did the earliest galaxies truly grow faster than astronomers once believed? The evidence suggests that some probably did. Exactly why they did so remains an active field of research. Perhaps dense environments accelerated their evolution. Perhaps the first stars differed significantly from later generations. Perhaps black holes, dark matter gas dynamics, and stellar feedback interacted in ways that current simulations are only beginning to capture. Or perhaps several of these ideas are true simultaneously. The universe is rarely obligated to choose only one explanation. That uncertainty should not be viewed as a flaw. It is a reminder that science is not a collection of final answers preserved forever. It is a continuing conversation between observation and understanding. Every telescope extends that conversation. Every generation inherits it. Every new discovery leaves another horizon waiting quietly beyond the last. One day, future observatories may detect the first population 3 stars directly. They may trace hydrogen across the cosmic dark ages. They may uncover the true nature of dark matter, or explain how the earliest black holes assembled so rapidly. They may answer questions that today seem almost beyond imagination. When that happens, the story told here will not become obsolete. It will become one chapter within a larger narrative. Just as Galileo's observations remain part of modern astronomy, today's discoveries will become the foundation upon which future understanding is built. That continuity is one of science's quiet beauties. Knowledge does not replace itself. It grows. Tonight, somewhere beyond the reach of every telescope now operating ancient photons continue their patient journey. Some began travelling before the first galaxies had fully matured. Others may carry information from epochs we have never observed directly. They are moving toward us even now, crossing billions of light years without pause. Perhaps centuries from now, instruments yet unimagined will finally receive them. Perhaps those distant beams of light will answer questions we have asked throughout this documentary. Or perhaps they will reveal mysteries no one has yet considered. For that has always been the nature of the universe. Every time we believe we have reached the edge of understanding, the darkness beyond quietly offers another dawn. And so we return to the thought with which we began. The early universe may not have been as simple as we once believed. Not because our understanding was wrong, but because reality has proved richer than our first descriptions could capture. The galaxies revealed by the James Webb Space Telescope are not challenging us to abandon the story of the cosmos. They're inviting us to read its opening chapters more carefully. Somewhere within those ancient pages written in light that has travelled almost the entire lifetime of the universe, the next sentence is already on its way.